Sharing full screen should do now. I will try to get rid of the chat for now and the list of participants. Can you all see my screen?
Yeah.
Okay, I actually can see some of you actually. Paco is here, I see him. I see Maria Victoria. Okay, cool. I'm gonna try to get my laser pointer. There you go. Okay, so we give a sec to the people setting up YouTube so they can make a start, and I'm gonna start in 1 minute. Alrighty. Very good morning, everyone. Hope you are well and safe at home. And so this is really unfortunate that for our very first general purpose AI winter school at the University of Granada, we are having to start online, and really sorry about that. My name is Isaac Triguero, and I'm a professor here at the University of Granada, and I will be one of the hosts for this week. Together with me, Professor Francisco Herrera here, Paco, and Maria Victoria Velasco have been organizing this winter school for the last 6-7 months. And so we are really disappointed that we are starting this online rather than in person, but hopefully from tomorrow, we're going to be there. Really happy to see so many of you. We really thank you for being here. And I would also like to thank all the speakers. We have a great bunch of speakers talking to us today and throughout the week, who actually many of them made their way to Granada. Hopefully some of them will be flying today to Granada and their flights will not be canceled. We will see that. Of course, I also need to thank our funding who have really helped to bring all the speakers here as well, right? And that wouldn't be possible. So before we make a start, I wanted to stop by and say who is here in the room. Before you actually tell me, I prepared this beautiful picture trying to show you where people come from today. Obviously, you can guess, I tried to make this picture, this plot with ChatGPT. It didn't quite work. Then I tried Gemini, and then Gemini, I gave it to ChatGPT. But finally, I managed to get something looks like a slide. And it forgot a few countries. For example, Poland is not in there. I don't know why. There was another country I don't remember right now. Like India is not there. At least the name is the ping is in there, but not the actual name. But yeah, generative AI is not far from perfect. We've got 38 registrations. Mostly people come from Spain, but not only from the University of Granada, but from different universities, coming from Pamplona, from Jaén, and so forth, and also people from different companies like Archimea and Repsol as well. We have people from Italy, United States, Cuba, Brazil, and many more, right? So yeah, what I wanted to do to start with is just basically getting to know each other a little bit. So I wanted to hear about your backgrounds, because I don't know for sure. I'm guessing most of you are PhD students, hopefully. You know a little bit about computer science, but I wanted to run a bit of a poll about where your background is, if that's purely computer science or statistics, physics, math, and so forth. Ivan was trying to use the poll feature from Zoom, but it didn't quite work. So yeah, maybe we can try to do the old school way of trying to say out loud or raising your hands and trying to see all your faces here. Although I only see a few people. So any computer scientists in the room? No? Okay. A few hands up. Yeah. Any mathematicians in the room? Same hands again. Oh, any physicists in the room?
You can try to react with the
Oh yeah, you can try to do the reaction. Yeah, physicist. No, you're not a physicist, Ivan. You're. Oh, there you go. Why did you get the balloons, Mario? And that's a reaction from
Yeah, I think so.
from Mac. I don't know if is there any other background I don't know of that might be related to what we're doing here today, since this session maybe perhaps someone from weird background like English or something, and they still want to learn AI, and it's not the first time that happens to me. All right, yeah, okay, we'll see. Hopefully, you know, from tomorrow it will be so much more easier to speak to each other and get to know each other a little bit better. But yeah, I kind of got the feeling that there are many computer scientists, a few mathematicians. Obviously, this will be kind of fun. So basically, as you can see from the very first interaction with you, what I wanted to say before we make a start is that this is not really a conference, right? So the whole thing about this winter school is for you to learn about general purpose AI. And that was the whole point. And so we are expecting interaction. We're expecting you to speak to us. And we're expecting this to be a bit more informal than a normal conference. And it's super fine to disagree with what I'm saying or with what any of the speakers are saying, especially general purpose AI is very much still forming, and therefore it's quite normal that we might disagree on what it is and the different things that we can do about it. There will be a wide range of talks, right? There will be people coming from more mathematical background and much more applied background, and there will be different levels, and it's perfectly fine. I think we need to acknowledge that from the very beginning. It's perfectly fine. We're not going to understand everything that the speakers are talking about, but that's why we're here. We want to try to learn something. We want to try to be able to at least being able to discuss what you don't understand, right? We also want this to be a networking space. There will be opportunities for you guys to share your research during the coffee break, not today, obviously, but poster sessions and so forth. And so that will be a very good opportunity for you to speak to each other, but also get to know the speakers if you have time. There are a few microphones still open. If you could please mute yourself, because that sound will come out on the YouTube video. Yep. Few housekeeping messages before we go. Obviously, we can make coffee for you today, and that's really unfortunate. You will have to make your own coffee, Israel, and he was pointing that out yesterday night. But, well, luckily, the company who are helping us to arrange the whole event, they managed to get lunch provided for those students at the residency and also for the speakers at their hotel. Obviously, for those of you coming from Granada who are staying at home, unfortunately, we cannot do anything about that. We are very sorry about that. We will try to compensate somehow. And hopefully tomorrow we will be in person and we will be ready to go. All right, so having said all of that, what do I want to do today is just to give you a really gentle, quick, generic introduction to what we mean by general purpose AI. And I would like to walk you through a transition from what I call traditional AI and use the word big data mostly to what we are talking about right now about general purpose AI systems. And at the very end, I will show you just a couple of examples of research projects that we are carrying out here at the University of Granada, and a few stuff about how this winter school fits in with the whole general purpose AI systems. Okay, all right, so we are ready to start. And obviously, I wanted to start talking about what are the latest advances of AI, right? And every time I think of that, and every time that my family or friends say to me, so Isaac, you work on AI, what are the latest advances? And I really wish I could say that this is the greatest advance in AI, right? So That's not really. And that was my book that I actually got on large scale big data analytics. I published in 2023. But the very same day I submitted my latest version of the book, the proof of the book, that very same day, this guy popped into the market. What is that? So that is basically an LLM created by Apache Spark that allows you to do basically everything I taught in the book, but so much more easily. And that was a little bit annoying to me, but I know for sure that at least for now, ChatGPT, Gemini, or any others do not know how to answer my exam because my students are still failing. So I'm happy about that. But I did feel a little bit like, oh dear, since November 2022, things have changed. And many people think that AI, will conquer the world, but somehow it's going, and oscillating a little bit between AI will save all of us or AI will conquer all of us. What I'd like to say is that, well, if AI is really planning to take over the world, well, that Python script that they have created is probably just waiting somewhere in a server, waiting for more GPUs to come online, right? So very much still quite soft takeover from AI at this minute. But it's very much true that these systems and ChatGPT and so forth have created a lot of hype and fears, and many people are talking about artificial general intelligence, right? That idea that they will basically take over and do everything that we can do. But one thing I can say for sure is the intelligence of current AI systems really differs from human intelligence. They are so much better than us at assembling patterns, at being able to calculate real quick. But at the moment, they are still not so great at complex reasoning, having any initiative, curiosity, and stuff like that. So I'm not going to go into that fight of what are we? Are we in this artificial general intelligence stage or not yet? But that's kind of the whole thing. We don't want that, but we want to actually say that intelligence is just simply different at the moment. Until not so long ago, before, let's say, November 2022, it wasn't all about agents. Nowadays, everybody speaks about agents, LLMs, and so forth. But before, we were more on that big data realm, where basically we follow this machine learning life cycle in which companies started, gathering information, and normally they started collecting a lot of data just for the sake of it, thinking, okay, we are collecting data and that data will be useful at some point. And then with that, they tried to use that for their business needs. But, well, they didn't know that data was really good. We went through that cycle of trying to model the data, explore the data, pre-process the data, select the best model, evaluate it, and analyze the results. And whenever we had something decent, we went and tried to deploy that for the business, right? And that was normally like a bit of a cycle in which we keep repeating, iterating, and improving. But the main thing is, to do so, we rely a lot and very much on having labels and having experts to do something and telling us if the system is working correctly. But then that is not helping us to generalize, right? And that's what we aim to. We actually aim to, with general purpose artificial intelligence systems, we aim to automate this whole process. Just to show you an example of what I mean by traditional fixed purpose AI, this is a project I was running back when I was in the UK with the company called Unilever. And what these guys actually make, well, what they make is ice cream, right? So you're probably tasted at some point their ice creams. And what they wanted to do is to put a camera in their cabinets, because they do own the cabinets, and they wanted to do image classification, basically being able to predict the stock level in that image that you're seeing here. So they wanted to be able to say, oh, there are so many Magnum here, there is this 88, whatever that is, there's Calippo here, and they wanted to know how much of each one of them they had. And why they wanted that is to be able to monitor real-time the stock level. And this is very much a traditional fixed purpose AI system in which we're going to need experts, or someone at least, to be able to label those images and say, well, in this image, I see, let's say, 30% of the stock in general, and then I see these different brands, right? And then with that, we will train a big network to be able to do the whole thing about monitoring and predicting how ice creams will be actually sold. Advanced models, the best thing that they can do is try to make use of any external data like footfall, people going through, going in and out of the shops, the weather, bank holidays, and so forth. But what we always found is very much always a problem on the data availability, especially big companies like Unilever. I don't know if you know the company, it's a really international big company. Data is always really unstructured, is kind of all over the place on different platforms, different data sets, spreadsheets, and so forth. And one thing we had all the time is whenever they change the camera, because they do have, and they were fitting in different cameras all the time, or they have a different cabinet. Sometimes the cabinet was horizontal, sometimes the cabinet was a vertical cabinet, and that kind of thing. We always had a bit of an issue. We had to basically retrain the model to be able to do a good job. And we always need some new labels at the very least to be able to adjust our model and to make it able to cope with the new situation, right? So that's kind of the main caveat for fixed purpose AI. It didn't really generalize and it wasn't ready for the next step. So what are these general purpose AI systems? What are they? Why are we talking about them? Well, when I came back to the University of Granada back in 2022, 2023, I started talking to Paco Herrera and the team. And what we noticed is that in the attempt from the EU, from the European Union, from the States, from the UK, and so forth, to regulate artificial intelligence, they started using that artificial general intelligence, general purpose AI systems, and all of those terms, they started using it like interchangeably, right? So they wanted to talk about AI being really sophisticated, but they were talking about AI like it can do anything. So for us, we went for that definition of what general purpose AI systems are, and we think of them as a more modest, realistic expectation of what AI really is, without expecting them to have any inherent human abilities. In the best case scenario, a general purpose AI system may be able to perform tasks it has not been trained for. And we will talk about that later on in the talk, but that's what we call emergent abilities. I'm not sure if you came up with that term before, if you came through that. Also, we notice that people are talking a lot, of course, about foundation models, generative AI, and they are a really important piece of the general purpose AI system picture, but they are not everything, okay? So that's what we noticed back in 2023, and we put together a paper basically trying to give our view on what these systems are, and we described that kind of in 3 different stages, from the fixed purpose AI example, like the one I was showing you before with Unilever. And we are here in this stage in which what we can do as well is to create new models to adapt much more quickly and to try to exploit any previous knowledge. But we are a little bit far, possibly, from anything to do with artificial general intelligence, right? When we work on this, it was 2023, published in 2024. We are already in 2026. Things are moving real quick, right? So our categorization, I think, is still valid, but things are moving on real quick. One thing we wanted to distinguish when we started looking at these systems is the way they operate. Some of them, they work on a closed world. A closed world is very much that idea of having all the books and having everything you need to be able to work. and therefore you know all the tasks you need to be performing, you know everything. So that's more like a multitask, basically neural network or whatever other AI system, but capable of dealing with multitask, multi-label, multiple things at the very same time. In that world, you basically try to exploit synergies across tasks, and you want to be able to solve all of them if possible at once, even though if they're not so similar. You expect to an extent for them to have sufficient training data to be able to do so. It doesn't mean that you don't need to use any data pre-processing, data augmentation, and so forth. It means it should be sufficient. However, in the open world, what you're looking for is a system that just goes and try to see if they can solve something they didn't know of before. It's basically no data at all, or sometimes just very, very few data that comes in, and you want that system to be able to cope with it real quick. And for that, of course, like human and we try to exploit anything we knew from the past, right? And that's where the terms emerging abilities comes from. It's the idea that sometimes actually these systems are showing abilities that they didn't know, that they were not programmed to do so, right? Quick stop at a couple of remarks about this closed and open world. And I think stopping about the data availability is really, really important because in that closed world, general purpose artificial intelligence systems, we do expect that sufficient amount of data. As I said before, pre-processing might be needed, but in the open world, basically having labeled data is going to be very much not possible, or just very few, right? Imagine that example from the cabinets that I was trying to classify images. The best I will be able to have in reality is for them to take a couple of pictures from the new cabinet, and now a vertical one, now with different ice creams, and they just tell me, oh, there is this ice cream, just one picture, right? And that should be sufficient for the system to generalize real quick. The little problem with the open world, which is obviously the most interesting one for this school, is that the systems may experience some difficulties, let's say. And one of them is obviously the one that we all know, hallucinations and true statements, sometimes having something real weird, and what they say, they come up with answers are not really right. Very much like students do when they take my exams, and they basically hallucinate and say something stupid sometimes, but sometimes they actually perform real well, even though I did not explain something, right? So that's what we would call an emergent ability. When we were doing this categorization, obviously we stopped by the idea of using multiple modalities, although this is not per se a general purpose feature. Is actually really useful to be able to process any kind of information, images, text, time series, and so forth, right? So here you have a funny image that I believe it went viral, in which an AI generated image, and then it went through ChatGPT-4 and it tried to describe what was unusual about that weird image of a person ironing a shirt at the back of a taxi, right? So that's a little bit awkward, but that ability to describe what is in a text is very much the idea of multimodality, right? When we thought of these systems back in 2023 or so, we were already guessing a little bit of, well, what's missing here? How do we make them more robust to avoid hallucinations and stuff like that? And we were talking about the idea of self-diagnosis, self-reflection, and all of those things. Obviously, not so long ago, people have been working on that since 2022, since they noticed. And one of the ways that you can use to improve the reasoning of general purpose AI systems, and especially, and might be useful for reducing hallucinations, although not the primary goal, is to use chain of thoughts, right? And I'm sure you heard of this before, and the whole thing about it is it's basically put an extra layer of AI on top to basically define the prompt that will be able to give us step by step the reasoning. So it actually learns to reason with previous examples, and then it tries to basically create prompts that will be helping the model itself to give a good and an accurate answer. And that has many benefits. Among them, obviously, is explainability, right? Now we are able to see a little bit of why the model came up with a particular solution. It might actually reduce hallucinations. And well, as you probably experienced already yourself, it actually is so much more accurate, right? There are different approaches. I'm not covering them here. Just wanted to mention that that's something expected, that advanced general purpose AI systems might go in that direction. So if you're still with me and you didn't go for coffee already, you might be wondering, so Isaac, what's next? How do we get artificial general intelligence systems? I wouldn't be able to say, right? So I wouldn't be able to say. I'm not gonna try to answer the question, but I do know that for now, complex reasoning is not there. Causality is still something it does not exploit really well. Curiosity, obviously, to explore new tasks. I do not think AI will tomorrow think of, oh, I want to learn to do something else. Still not yet, or having conscience about themselves. Okay. So if you're still with me, let's move on to how are they built. All right. So in our work, we tried to define a taxonomy of how these general purpose AI systems work. And again, the whole motivation for us was the idea that people thought of general purpose AI systems as LLMs only, right? And that's not really true. What we here define as two different approaches are different to an extent, obviously, because there is a lot of overlapping among the two, between the two approaches, obviously. But one of them is that foundation model kind of solution that is just a single model that is actually able to perform a variety of tasks, right? And some of them are purely foundation, some of them are not even foundation models. But the other category that we define here in our paper is what we call AI power AI approaches, which is basically the idea of adding an extra layer of abstraction on top of the AI. So an AI algorithm that will be helping designing or enriching another AI. I'm going to stop by that in a sec, but obviously many of the techniques that we will see in this course actually belong to this category to automatically design new machine learning algorithms or to generate artificial data, right? So stopping by the first concept, the idea of foundation models, and assuming that you may know this because you already work on foundation models and this is completely trivial for you, but if you were to be completely new to the topic, I just wanted to stop by and tell you what I believe is the key thing, right, about foundation models. How do they work? They basically train models on really, really large amounts of data, and typically for many, many tasks, right? And whenever we have some particular task to solve, we might be able to fine-tune them. And this is very much limited to deep learning and the idea of transfer learning. But if you were following me from before, I did say before, when I was showing you my example from Unilever and the classification of ice cream, one of the things is, well, you need to have labeled data. You need to have ground truth to be able to say if the system is working or not. So how are we going to train on really large amounts of data? Well, here is when the concept of self-supervision comes into place. Really, really important to use something that is able to use unlabeled data successfully to train a really big model, right? So how do we do that? Well, we can do semi-supervised learning, but we can do self-supervision. If you're not super familiar with that idea, I wanted just to give you a flavor of what that is. How does ChatGPT actually train? It has, let's say, all the text of the internet. How did it actually have any labels? It did not have labels, but it used like a pretext, we call it a pretext task, which is basically inventing those labels and that task that we want to do. Basically, imagine the following text that you see here on the screen, and we create artificially a task that is predicting these words that we delete intentionally, right? So we mask them out, and then we train a model to be able to predict what is the word here, here, and here. And that, of course, is now a label classification prediction problem, right? Same thing for images. You can just take an image and you can mask out some pixels, and you can then train a model to be able to predict what is missing here. Somehow we have converted a fully unsupervised problem into something supervised that is not what we want to do. We want to be able to speak, right? But predicting what is missing here is actually helping a lot to do that, because basically you're predicting what is missing here. Next time around, when you have a sentence, you can help that, you can use that idea to predict what is the next word, which is basically how LLMs very much work underneath, right? So that's the whole thing. But there is a completely different approach that we will have in a few hours, actually 1 hour, from our very first speaker, Frank Hutter, which is the idea of, well, I do not have labeled data, but how about just basically create artificially generated data that is supervised, and we can train our models there. And that PFN V2 is a really great example of that, right? Within foundation models, if you're still with me, the idea of mixture of experts, you probably heard of that, especially when DeepSeek actually came into place. And it's the idea that, yes, we do have a single model, but we are going to have subsets of the network to specialize to do different tasks, right? And that way, you can activate only part of the network whenever we need to answer a particular question. And that's what made actually DeepSeek so much more efficient than dense models like GPT-3, that it has to use the entire network to make the prediction. So it gained a lot of efficiency and ability to scale up nice and easy, right? So I just wanted to stop by and mention that just to give a little bit of a general picture of how these systems work. So that's single model, and that's the first category. And the second category is, of course, the idea of using AI to do AI, right? So, of course, I guess the easiest one to think about is hyperparameter tuning. We have all done that. It's just basically a search algorithm, an optimization algorithm, or machine learning based algorithm to be able to predict hyperparameters. But it could also be used to predict which model is going to be better. Previous AutoML solutions like AutoScikit-learn, for example, was based on that idea of using meta-learning to decide what is the best model for this particular data, or even to design models from scratch. As we will have a few talks and in here from Jinshu, I believe, and Rui, they will be talking to us about automated algorithm generation. But you can also use AI not only to design AI, but also to help them mitigate basically the main challenges that they experience. In many cases, we are going to experience that the systems and the data or whatever task we need to do is going to change. And that's more like data stream type of thing that Joao Gama will be covering in this winter school. Just the ability to do more continual learning. That is also something that will be covered tomorrow by Simone Calderara as well, right? So that kind of ability to cope with changes, that's really important in AI, and you can actually predict that kind of change with AI and try to tell the model when to readjust if possible. Of course, data generation is a way, as I mentioned before. Learning to learn is the idea of meta-learning, which is really useful to be able to learn more quickly, learning to do and solve different tasks. Active learning, where we get the human in the loop somehow. And the last but not least, actually, because I believe it's one of the most interesting ones, is the idea of different AI systems collectively and cooperatively working together. So I wanted to stop by here because we will also have a few talks that are very much related to this throughout the school. And the whole goal of these systems is obviously try to mitigate the weaknesses of isolated AI models, right? So the whole thing about collectively putting together systems and already develop machine learning AI tools is to try to make them, all of them, more autonomous. So we're going to put an extra layer that will decide which of our subsystems should be interacting or actioning to solve a particular problem. One prime example of that would be Learnware, which is the software and the idea that Professor Joe will be presenting on Friday morning, right? But it's not the only thing. The idea of collectively learning could also be the idea related to the idea of model merging, which is basically the idea of I have a model capable of doing X, Y, and Z task, and I have another model able to do different tasks, and we try to merge their knowledge into one single system, right? So that kind of thing is what we are talking about when we talk about cooperative learning. Here you have a quick overview of how the system that Professor Joe will be describing so much more in detail on Friday, I believe. But basically is you have a number of models, but together with the models, what they suggest is that the models should come together with some sort of specification of what they're good at, right? So at the end of the day, you can see that for me as some metadata that will tell you, okay, I have this method that was trained in this way with this data. It performs relatively well like this. And then whenever you have a new task, basically you're going to check which of the models will be the best idea for you to use, right? So they have come up with a system. I'm not gonna detail everything because I don't want to spoil what Professor Joe will be explaining on Friday, but that's kind of very much the idea of collaborating and with multiple AI systems. And when things get a little bit scary, obviously, is that kind of idea of agents that already with ChatGPT 3 started, we started seeing things like AutoGPT, Meta GPT, and so forth. And that's when basically you get an agent that will be basically deciding what to do next and asking the AI to do the next step and so forth, right? So here is a classical example of, okay, let's use LLMs to get to program the whole game of the snake, right? So start asking, okay, what do I need to do to implement that? Okay, I got the instructions, then I use those instructions to go step by step and asking it again and again and again, but all of that created automatically to actually generate the code and get everything done and working. And it does actually work. That's when things get a little bit scary because they can actually automate and become more independent systems. As I mentioned before, mixture of experts, of course, I wanted to mention mixture of agents, that you probably heard about that terminology before, which is a very similar idea to the one we explained with the experts. But before it was a full network and subsets of them specialized to do different things. The idea of mixture of agents is very much different, complete different models that are all then interconnected and they do collaborate, and you need some sort of orchestration mechanisms to be able to organize them together, right? So there is plenty of research in that direction at the moment. Okay, if you're still alive, I just wanted to end up this kind of description of the taxonomy and all this stuff, stopping by the role of evolutionary computation for general purpose AI. Because basically here in Granada, we've been working on evolutionary computation quite a bit of time. We decided to investigate a little bit more and to study how this, let's say, strategy to optimize stuff could be used to design and enrich general purpose artificial intelligence. And we put together a paper that is now published in Transactional Evolutionary Computation, where we actually explore what do we want general purpose AI systems to have and how do they relate to evolutionary computation. I'm not going to go into any detail, but because we're going to have plenty of talks actually about that. I originally programmed all of them for Friday, but because of the situation today, I will show you later on that I had to move a few talks from Dave. Okay, all right. So let's start off with some of my own examples, right? So I'm not going to go into much detail because actually the two projects I want to mention today are projects that are very much initiating. And if you have any questions, I have my PhD students here who are working on that already, right? So in this project, I'm gonna basically introduce to you guys is a project that my PhD student Alberto is working, and also Jaime from the University of Granada are working on. And the idea is to use general purpose AI systems, but when you need to do something really specific in which the robustness and the quality of the answers are critical to make sure that everything goes smoothly and nicely. We are building in Granada a particle accelerator. That's a mistake, a typo in there in the slide, sorry. And a particle accelerator is being built and actually expected for 2030, I believe. So sorry about that. There is plenty of mistakes on that very first sentence. So that particle accelerator is being built, and we are now working on the AI that will be around that particle accelerator. And the whole thing is, it actually falls short from the very beginning. When you start looking at anything to do with physics and so forth, and you try to use a general purpose LLM like ChatGPT, it will fail, right? So same, and like you may experience already with ChatGPT, you try to do some math and maybe they're not so good at that, and that's why they're doing a lot of complex reasoning and all of this chain of thoughts and tree of thoughts and so forth. It's very much the same thing, but here we need that to have a very specialized knowledge of physics and fusion-like energy and all of this stuff, right? So what we want to do is to create a general system, sure, but we want to start off from a general system, but we want to specialize that general system into something really, really important. And for that, we believe in here because this particle accelerator will have so many different phases and so many things that we need to do that is a perfect use case for agentic AI. And that means that we're going to have so many different programs all together trying to solve the different things that we need to predict, forecast, describe, and so forth, right? So we're gonna need some sort of orchestrator that will be saying, okay, the person is asking me to do this. So imagine the main person responsible for this coming into the particle accelerator and simply saying, hey, what's up? How are things today? Is there any anomaly? Is there any problem with the experiments? And or I have this question about a particular physics, whatever question that they may have about the experiment they are running, right? So all of that need to be answered by the whole system, and that will collaborate together to try to do all of that and be able to basically delegate the task to the right part, right? To build LLMs that will be able to, let's say, interpret correctly all of the things that we need for specific situations like this. Obviously, we may need to build some strategies, fine-tuning strategies for that particular type of text, or retrieval augmented generation stuff, and things like that as well. Okay, so just wanted you to know that we're working on that, and if you have any interest, we could discuss. And the last but not least is a project that we started, well, very much actually got accepted last week. So this is an European project that will be beginning in September this year, that is all about the idea of emerging abilities. As I said before, the idea of emerging abilities comes from, well, sometimes it has actually surprised us how well these general purpose AI systems actually work, right? Prime example, I think it's the easiest way to understand this idea of emerging abilities, and what we aim to do here is, if you think of the idea of in-context learning, I'm sure that probably that terminology you heard before, this is the idea of using the prompt and whatever you give to the system to be used to learn something and be able to give a better solution without any training, some sort of zero shot ability to forecast, predict, and actually interact with the query directly itself. That idea of in-context learning, that was something that was latent in GPT-3. It was there, the building blocks to make that happen, it was there, but it was not like it is today in GPT-5, right? Today is a reality. You can simply explain something to ChatGPT and it will actually learn it, right? And we'll be able to use it afterwards to do so. What we here say, or what we want to do in this project, is to be able to predict that kind of emerging ability, because they will help us a lot to do any sort of regulation and try to know what kind of ability and capability might be present in the future and how that is aligning with human intent, right? So I think the main open questions that we have at the moment is, what is exactly an emerging ability? This is just one example. And also, how do they happen? Do they happen randomly, or they happen just simply because we have more computational power? So all of those are the questions we are trying to solve in the next 3 years, and that's the whole project about. And if you have any questions, my postdoc here, Leonardo, that I believe should be somewhere here in the room, he should be able to explain to us a little bit more about it. But I think something interesting here is sometimes, because basically the system trains with so much more data, we have that illusion that it just happened. But what we believe is that the building blocks were already there to be able to do that kind of task, right? So hopefully, with that very short introduction to the system, to the general purpose AI systems, you got into your head a few things that I want to check, and that is that large language models and vision language models as well are currently what we see of general purpose AI, obviously, but they are not the only thing, and there are so many more things that we could do. At the moment, people talk about hallucinations, complex reasoning, the idea of emerging abilities, and of course the idea of giving more autonomy to these systems. This is just a term. I don't know for how long it will be out there. Maybe in 10 years' time, like big data is not fashionable anymore. Maybe general purpose AI systems is not fashionable anymore, and we have something else. We call it maybe agentic from now on. I do not know. But for us, it's just simply a more modest vision of what the current AI systems can actually do. And something I really want to emphasize is, even though we say general purpose, it does not mean no specific solution. Sometimes we do have to start off from that general model because it has trained with so much more than just one single specialized solution from the very beginning. Sometimes, and it's been demonstrated that in many cases, pre-trained stuff do work so much better. And because general purpose AI systems is not all about foundation models, and it's all about also AI to power AI, we believe that the machine learning and optimization communities have a lot to say on the development of AI. And many things that we've been working on in machine learning and optimization to generalize might still be useful in the new context and the new paradigms that we are dealing with at the moment. The main difficulty is to keep up with the current trends. All right, so that was basically my introduction. I just wanted to show you very briefly what we have for the next 5 days and one single general purpose story. When I put together the program, I need to acknowledge that I did think carefully of, okay, day 1 is going to be like this, day 2 is going to be like that, and so forth. And I could maybe tell you what I aim for, but of course, because of the weather situation, we had to change. And what I planned for today is I managed to get everybody who was actually anyway gonna deliver their talk online. They will be delivering their talk today. So we've got our very first speaker, Frank Hatter, joining at 11. He was joining anyways at 11 online, and he will be talking about tabular data and foundation models for that particular kind of data. That was the topic I chose for today, but that has changed a little bit. And then we've got Binshu, who is today in New Zealand. So it's going to be 2 a.m. for her, and she will be giving us a talk about evolutionary computation and general purpose AI systems. And last but not least, we've got Anurag coming from Google DeepMind, who is going to be talking about vision language models, LLMs, and beyond. That's what we have for today. This talk is a little bit shorter. It was scheduled originally for 45 minutes. So I thought that, for a day we are all in front of our computers. Today it's gonna be a little bit shorter than normal. So by 5, we should be finished today. So you can chill and maybe try to go out if you dare to go out and under the rain. For day 2, currently, this is how the schedule is looking like. We will have the opportunity to learn more about foundation models in images and video. We will have Professor Hanji explaining a lot about how to reuse pre-training, Simone talking about continual learning and also about model merging and so forth. And we will also have Shreyan from the University of Nottingham talking about zero-shot learning, which is something we also work on here, and we have some of our PhD students on that topic. But I thought Shreyan is going to give us a great tutorial, actually, tomorrow with a practical session. So I will let him explain what zero-shot learning is if you don't know it. Day 3, it was all about evolutionary computation, but because of the move, there will be the majority of it about evolutionary computation. Professor Joe will be talking about this LearnWork, which is that collective system that I mentioned before. We've got Jamal coming from Malaga and MIT, who is going to be talking about general adversarial networks and evolutionary computation. Stephen, who will be probably talking about contrastive learning and so forth. And last but not least, Ruijan, who is going to be talking about automated algorithm design, right? Then if things go well, we will go to ski on Saturday and Sunday, but then on Monday we come back to a little bit more math-oriented part of the school, right? So in that part of the school, Maria Victoria will be taking over a little bit from me and being the host for that part. Shared will be talking about kernel Banach spaces, Julien coming from INRIA as well, talking about deep learning, kernel methods, and so forth. And it will be at the end when Joel Gama actually will be talking about data streams and learning from that kind of time evolving data. And the last day, we will be covering a few more aspects, a little bit more, mixing a little bit data difficulty, explainable AI, and also interacting systems from a math perspective as well. We have a discussion panel at the very end, and we will have plenty of poster breaks in which if you guys already sent to us your poster, it's already printed there and it's there in the building for us to chat about our research and use that as networking opportunity asset. But it's obviously not all about work in this winter school. So hopefully we will be able to go to Sierra Nevada on Saturday, but if not, we will just basically go to the city center and explore Granada. That's what we like to do over Saturday and maybe Sunday as well. So that's very much it. I had a bit of some advertising to do, just because my friend Shinyu is also here as well. We put together, Shinyu and myself, we put together a task force with the IEEE Computational Intelligence Society. It's a task force about LLMs and computational intelligence for this kind of systems. And we're going to be organizing quite a few things. If you are in the community of computational intelligence, you might be interested in having a look at the website and having a look at what we are organizing. At the moment, we are working on a technical challenge about how to make LLMs more specialized for particular things, right? But we will also be doing special issues, special sessions, workshops, tutorials, and actually this kind of seminar we're doing today is part of that task force. Just to end with some acknowledgement because I have to. And here it is. And I just wanted to say thank you, everybody. Thank you for being here, and a few pictures of the team that work with me. And if you have any questions, we still have a few minutes. So let me end the show and we'll stop sharing for a sec.
Yeah. I don't know if you answered the question that Carlos was writing about LLMs look like are a subset of GPAIS. Did you?
Let me see. Can you repeat the question, please?
The question is, if I understand correctly, LLMs are a subset of GPAIS. How much of the research do you think is focused on LLMs as GPAIS, and how much for the rest? So, I mean, it's in the also. I cannot think right now on examples that are not based on LLMs. I'm especially interested in non-LLM systems that has these emergent abilities. Also,
that's a really great question.
Carlos is actually on the deck, so if he wants to watch something, he can.
Yeah. If you want to show your face, Carlos, that's also an option. But really great question. And obviously, it feels like LLMs are the only thing. And that's very much because LLMs have become the voice of the AI, right? The way to communicate with us. It has the language. And it will be, I think, in any real general purpose systems, it will be there. And we have to speak to it. But LLMs per se, you're not able to do everything, right? So you might need to put some sort of AI system on top to coordinate what the LLM is doing for you, right? So an LLM may be trying to directly do tasks, very specialized things like anomaly detection, for example. That might not be as simple, right? Or just simply solve a machine learning classification task. It's not as simple. It cannot do that so easily. That's how I see things that are not purely LLM, and so we have to work on that kind of extra layer to make everything work. But what you did say about emerging abilities, I fully agree with you. Emerging abilities have been seen on that kind of neural net that are LLM based, right? But you can also maybe find out that a transformer that was trained to do a particular thing might be able to explore some sort of emerging ability that you were not thinking about. I believe here in our research group, for example, I'm just speaking from the top of my head, but I believe there is some work here about transformers for chess and playing chess. And it has shown, for example, that kind of transformer has some sort of an emerging ability, just to say, because it came up with strategies that do not exist in the literature, right? So you could say that's an emerging ability, nothing to do with LLMs. I'm not sure that clarifies your question, Carlos, but that's random answer from me as I speak to you guys.
Also, maybe talking about this too, probably what we're talking actually about is about the agent AI focusing not more in the LLM as a structure, but as small agent, as a good agent. And at the end, this macro agent that the word used in the literature is like orchestra, could also try to develop a new small agent that it could be just, let's say, a usual MLP for specific questions, and you don't need to ask. You don't need to specialize with a big LLM, but a small problem solver, and you don't need an LLM for each of these agents. So
definitely possible, right? So yeah, the whole orchestrator asking the LLM to write the code to do another agent that could be incorporated to the system. That's definitely an idea that is doable, and it will show obviously emergent abilities. But that is, I would say, that's kind of impossible to predict because unless it's all aligned with human intent, what do they want to achieve? Is that even possible? That's what you want to predict. Any other question, everyone?
Oroel says that version 2, version 3 models are an example of models with emerging properties in computer vision, not related to LLMs, for example. Just, it's kind of fun.
Yeah, another example of transformer-based stuff that are able to do things that were not directly programmed to do.
So if there's no other question, maybe we can start the break, the small break till 11, I think.
Yes, so we're gonna meet Frank in about 20 minutes, 25 minutes. Thank you very much for all of you for coming. Hopefully that was okay-ish. And even though we were doing this on Zoom, that was understandable. If you have any questions at any other point, just let me know. We also have the Telegram chat and anything we need, okay? So I'll see you guys in about 20 minutes or 25 minutes. So we welcome Frank. Fantastic. See you in a bit.
See you in 10
I'm gonna make coffee for myself.
Me too.
Thank you, sir.
Thank you.
Very good talk.
on YouTube now. So I'm going to make a very quick intro of Frank and then we go ahead. All right. So yeah, welcome back, everyone. It's really a great honor to introduce Frank Hutter. Frank is a professor at the University of Freiburg. I hope I pronounced that correctly. He is a recipient of an ERC Consolidator grant, which is essentially a way for the European Research Councils of saying that he's so great at what he does that he couldn't say no to him. Many of us, like me, I was studying his work, his pioneering work on how to automate machine learning, only for Frank to decide that that automation was not fast enough, and we actually needed some foundation models instead. He's achieved the impossible, and I was really, really happy about him making tabular data cool again. Unfortunately for us, although I've been working on tabular data for a very long time, now it feels like a really bit challenging, to beat TabPFN, if at all possible. So yeah, thanks for that, Frank. Thank you again for joining us today and for making our research life both easier and much more competitive. We thank you, and you have the floor for yourself. You've got plenty of time. We have scheduled 2 hours, so I know you have 1 hour and maybe a demo after, but feel free to spend as much time as you want interacting with the audience as you like. The floor is yours. Thank you.
All right. Yeah, thank you very much for the warm welcome and for the introduction. I guess I don't have to apologize for being online anymore. So glad that you're all online. Yeah, so today I do want to talk about this foundation model revolution for tabular data. I come from AutoML. That's what I've been doing for, like 15 years, really pushing AutoML, AutoML workshop series, AutoML conference, etc. And in the end of the day, AutoML allowed us to build great systems such as AutoSKlearn, and with this, and we've been thinking a lot about foundation models with AutoML for like 5 years. I've also been working on, how to use AutoML to make foundation models better. But this year is on basically using foundation models for the same problems where we used to use AutoML. And of course, AutoML creeps back in left and right, and you can build ensembles and post-hoc ensembling and so on. So this is by no means to say that, this replaces AutoML. It's just a different, faster approach to the problem. And whenever you hear agentic systems, I would like you to think AutoML in the future, because this is really what this is. And there's no difference in what people are doing in agentic systems. It's just not called AutoML, but it's sort of an automated ways to make machine learning easier and better. All right. We do have a startup now on tabular data, tabular foundation models. This is Prior Labs, and this is where I am actually now, 100%. I'm on leave from the university, and I'm still also affiliated with the Ellis Institute in Tübingen. All right, let's get going. So if you don't take anything away other than one slide, make it this slide. So after years of false promises, deep learning finally excels for tabular data. There have been like years, probably 5 years of promises where deep learning methods said, oh, here is a new state-of-the-art benchmarked on one data set, and we beat XGBoost, and then you run it on any other data set and it just fails. This is a thing of the past. With tabular foundation models, really in the last year, we have seen many different deep learning methods all published within the last year that like here's 7 of them on this benchmark Tabarina that clearly outperform the previous methods. Like here's all the boosting methods like GBM, CutBoost, XGBoost. They're all very solid methods from sort of 15, 20 years ago, but they've carried tabular learning for a long time. And that's why, of course, they're super ingrained in the community and people love them. But probably this is going to swing fully in all of tabular right now. So this benchmark here is on up to 10,000 data points. I'll later have a slide on 100,000 data points. If you have 10 million data points, you might still want to use traditional methods, but I predict that within this year, there's not really going to be a size constraint where tabular foundation models can't compete. All right, moving on. The good news is that the success on these benchmarks actually does transfer to the real world. So TAPIFN v2, we published in Nature last January. And since then, there have been over 500 papers citing that Nature paper. And from those, we actually collected over 100 use cases where we had nothing to do with them. People just downloaded the open source model and used it for some problem and reported improved performance. And this was a lot of these use cases were in healthcare and life sciences because the limit here was 10,000 data points, and healthcare and life sciences often comes with small data sets. Finance is something where we see a lot of commercial success with Prior Labs, but nobody publishes in finance, so we actually only saw 3 data sets here. Then energy and utilities, manufacturing, industrial, other industries, like it's really super horizontal, very broad in terms of the applications you can see. All right, Prior Labs, here's sort of like my one slide on Prior Labs. So we are the Tabular Foundation Model Company. One of our co-founders is Bernhard Schürkopf, who is a director of MPI and Ellis, the most cited scientist in causal ML worldwide. We also have Jan LeCun joining the scientific advisory board last month, and Madeleine Hulsebos, who's super great in table representation learning. And we actually managed to build up a great startup in Europe that attracts people from everywhere, from across the world to move to Germany, from all kinds of different universities like MIT, Oxford, etc., but also from the hyperscalers, Google, Apple, Amazon, etc. And I'm super excited about that. Let's leave it at that and look at the outline. So I want to talk today about the motivation for tabular foundation models. Why do we actually care other than just performance? Then I'll talk about TAPIFN a bunch, and then also talk about some exemplary use cases, and we can have a look at the demo in the end. I don't think I will walk through the entire demo, but there's the collab, and I'll just show that it exists, and you can walk through it offline. All right. So the foundation model revolution, we all know that foundation models transformed text and images entirely. Our life is not the same anymore with ChatGPT. Also in images, well, if you're a computer vision researcher, your life is not the same as it was 10 years ago. Things really changed a lot. And for tabular data, this hasn't been the case at all. Yet at the same time, in enterprise, this is where the most valuable data actually lies. Or if you're a scientist, then you have tables, time series, databases, etc. And this is a big gaping hole that we're aiming to fill with Prior Labs. Just to make sure we're all talking about the same thing. What is tabular data? So here's a concrete example from medicine. Medicine it's really amazing what people can do these days. So people can take your blood and then just look at some omics blood markers, and from that there's actually a strong correlation with having certain diseases. And so we could, for example, have this data set where we have 5,000 patients, where we have these 4 different omics blood marker values, and we know this person actually then developed Alzheimer's and this person didn't. And we know that for these 5,000 previous patients, and for these new patients, we know the omics blood markers, and we don't know. We want to predict, do they have early stage Alzheimer's or not? We can wait 3 years, then we know whether they had it, but then it's too late to treat it. So we want to predict it right now. And this is really sort of the decade-old problem formulation many of you saw in sort of a first machine learning course, where you would learn decision trees or random forests or SVMs or boosting methods, etc. And sort of this boring problem is just so widespread. There's thousands of examples like, will this treatment here work for this patient? Or in material science, how strong would a material be? Or in science, what type of galaxy is this data? Which product will this customer buy? Will this credit be paid back, etc.? There's a lot of value in this as well. And this is, of course, and wearing my prior labs hat, the value is much clearer than for LLMs. LLMs are super promising, but if you're an enterprise, well, you might use it for doing your email, but like you're not going to use an LLM on your enterprise data. It's just not working. And what you want to work, what do use is tabular prediction models. And if you can really improve the prediction quality there, there's an immediate dollar amount to how much that will improve. And so there is much more hunger for better tabular prediction models. Likewise, in medicine, you can use LLMs to predict what drug will work for a new patient, but yeah, that's not going to work. And again, if we can actually develop better machine learning methods, tabular prediction methods, that really brings a lot of social value, social good in improving the way that we can all be treated. All right. Closely related to this tabular problem is time series forecasting, where it's sort of even clearer what the training data is. It's just you have this time series over time and up to here, and then you want to predict the future. So this here is the training data, and that's the future. That's a test. And there you might want to predict stock prices or energy prices, solar energy production, demand, machine temperature, call center volume, etc., etc. So also a very common type of problem. And as I'll show later, these two are very intimately connected. You can actually cast time series as a tabular prediction problem. So why do we want foundation models for this tabular data? Well, in traditional ML, if you have multiple data sets, then you do a training run for each of them, and that gives you a model. But that, in like 4 different data sets, 4 times the effort. You have 4 different data science problems, and you end up with 4 individual siloed models. Each of them takes a lot of time in pre-processing and feature engineering and sort of like all these data science problems. If you have a really experienced data scientist, it might take a couple of hours. If it's a tricky problem or the person is new, it might take months. And the goal is to actually get to a foundation model where you once actually took a lot of data sets and you did one pre-training of a foundation model. And then you have this foundation model like a ChatGPT, and you feed the data you have in the context, do a forward pass, and get a prediction immediately without any manual steps. So that is the promise of foundation models. And this can also be fine-tuned. So if you have multiple data sets from a particular domain, you can also take the tabular foundation model and fine-tune it to your data, so to customize it to your data, and you get positive transfer across the data sets from a domain. All right, our community is on its way to revolutionize this tabular data. So with TabFN v2, we already showed more than 96% of the cases can be improved from previous methods. Only 50% of the data is needed for the same accuracy. So if you run a patient cohort and you needed in the past 1,000 patients for statistical significance, maybe now you can actually get away with 500 patients. And that immediately reduces the time to market for medicine, reduces the need for the randomized control trial to take too long, for finding the types of patients you can actually include in the study, the cost of this medicine that in the end, and also sort of the ethical cost of withholding a medicine that obviously is helping because a randomized control trial isn't done yet, and you need to not give this medicine. So this is it will be really helpful if we can remove some of this complexity and actually get away with less data there. And we release this as open source. We have more than I think now 2.6 million downloads, open source with over 6,000 stars. And there's a lot of companies are using this, and of course, a lot of universities. All right. So hopefully you're all motivated for tabular foundation models now. And next, I'd like to talk about TabFN. I'll talk about it in various dimensions. So first, I'll actually talk about TabFN v1. This was a project from 2022 that actually was, was not a usable product as such, but really showed the promise of tabular foundation models. And then basically we took that and made that a proper system that data scientists would like to use. And that is TabIF NV2 that was in Nature last year. Then I'll show that this can be used for time series. And then since this is a neural network, in tabular data, people are often quite worried with neural networks about interpretability. There I'll show that actually interpretability is better than with tree-based methods. And then I'll talk about some novel capabilities, robustness, outer distribution, fairness, and causal reasoning. And then also talk about some exemplary use cases and show demo. All right, let's jump right in. So this is a one-slide overview of how TabIFN works. In terms of the method, if you don't take anything away but one slide, let's make it this one. So on the left, we see the pre-training. On the right, we see the inference. In the pre-training, we have this TabIFN model here, which is a neural network parameterized by some parameters theta. And in contrast to traditional neural networks, the input is not just the features of one data point, but it's the entire data set. So it's a set-valued input where you take the entire X train, Y train, X test, and feed that to the neural network. This here is a question mark that you actually want to predict the Y test. So we take that out here and use it to score the output of the TabIFN. So that TabIFN outputs predictions for this, and we use a Y test to see how likely is the Y test under this predictive distribution here. That gives us a gradient signal for backprop. So we backprop once for this entire data set. And then we throw this data set away, we get a new data set, and we do a forward prop again. And initially, this TabIFN is untrained, it makes horrible predictions, but then the gradient signal is pushing it into the right direction. And we do this hundreds of millions of times until actually for a new data set, the TabIFN makes the right predictions. So you use the power of neural networks to and of modern optimizers to actually just really be able to find the global minima in this, or maybe not global minima, but very good minima in this high dimensional space of parameters theta. And to take that away, it's actually not that super high dimensional. It's a pretty small network. It has like 11 million parameters. It doesn't have trillions of parameters, very different than LLMs. It doesn't need to encode world knowledge. It encodes the statistical learning. So it encodes sort of patterns of data. If you see these types of patterns, then I can compute these types of features based on top of that and sort of, in the end, actually make good predictions. So you have an algorithm that actually lives in the weights of a neural network. And just like you execute the code that a person wrote for XGBoost, for example, here you execute the algorithm that was learned across hundreds of millions of data sets to work well, to actually optimize this test loss. And you can look at this test loss for all of your hundreds of millions of training data sets without then actually overfitting, because for a new data set, of course, well, you can't look at the Y test. For a new data set, you still, where you would do AutoML, you would actually split this into validation and test, and you can, of course, still do that. There's still also a couple of hyperparameters that in the inference that you could change. But the nice thing is here, this is actually optimized to minimize our cross-entropy loss on the test set. And as such, it actually overfits a lot less than your traditional tree-based models or AutoML, etc. All right, so this is all fine and good. If we can actually have hundreds of millions of data sets, and then in practice, we get a new data set. So on the right here, this is the first time we get a real data set. And we just take this and just forward prop it through the TabIFN, we get predictions, and that's our prediction for Y test. So same interface as during pre-training, and as such, we can expect very good predictions. And so if our hundreds of millions of data sets here are representative for what we expect later on, then this is sort of clear that this shall work. If we believe in deep learning, if we believe in the architecture as being able to actually properly capture this, and the optimizers to actually find a good minimum of the response surface, then this is bound to work. So the question then is really, how do we generate this synthetic data that resemble the types of data sets that we see later on? And often people think, oh, they're like, you use a small data set and then you generate more synthetic data like the small data set. That's not what we do. That's what a lot of other companies do, is sort of this privacy preserving types of synthetic data generation, where you generate data that is like your private data that you can give away. That is also synthetic data, but that's not what we do. We generate synthetic data from scratch that has the types of statistical patterns that we actually do expect in real data. And basically, what we did in order to build TabBFN is actually iterate on this prior generating process. And where we ended at is actually integrating principles from causality. So in particular, we use structural causal models, expecting that typically these tabular data sets have some sort of structure, a causal structure, where some features cause each other, or some features cause a response, or maybe the response causes some features. We don't know, but we're just going to sample many data sets with different types of characteristics and learn to pick the right characteristics. So we sample and initialize a causal graph with some edges in there. It's not fully connected. And then we sample where's the y going to be, and where are the x's. And it's not always the case that the x's causes the y's. And then we sample connections there and activation functions. So in the end, this is actually just a PyTorch graph. And the inputs actually of this can be sampled to generate data from this function. So this here encodes a function, and then we sample from this function several times. So we sample these noise variables that are the root variables, and then forward prop them through the graph to basically give us these values. And then we just read off, well, this is supposed to be the y, this is supposed to be the x1, that's supposed to be the x2. And there we have sampled a data point from this function. And then we have done this 2 more times. So we have 3 data points from this one data set. And if you have a classification data set, then, well, we might have some threshold here. So then we have a binary classification data set with 3 data points. In practice, we sample millions of these data sets. So for each data set, we sample a different causal graph, and then sample thousands of data points from this. In the sampling, we also have a prior that we encourage simplicity. So if we have only 2 features, then we could sample graphs with these 2 features and a y, and no latent variables. We could sample some with some latent variables, or we could sample some with many latent variables. But in the absence of extra information, we actually want to be biased towards simple explanations. It's sort of a type of doing Bayesian's Occam's razor. So we do want to push more likelihood on the simpler explanations with a less latent variables. And then we generate data sets, and they actually look very much like the real data sets. So here on the, just plotting one feature against another feature. And in this case here, binary classification task, where you have this orange class and the blue class, x1 versus x2, x1 versus x3, x1 versus x4, etc. And all that this slide is supposed to show is that these synthetic data sets on the left, actually, I can't quite tell if they're statistically different in their properties than the data sets on the right. So if we can generate millions of data sets that are like real data sets, and then we partition the space, like we take some of these data points. Whoa, what just happened? I'm sorry. I pushed the wrong button. Let me reshare, I guess. Somehow I closed my presentation by pushing the wrong button. Do you see the slides again?
Yes.
Okay, my apologies. I don't know where it was. I think I pushed stop share up here. Yeah, so where was I? Yeah, if we manage to generate many of these data sets that are like real data sets, and then we call some of the points training data points and other points we call test data points, and we manage to make the right predictions for the test data points, well then, if we then actually see a real data set like on the right, odds are that we're also going to predict well for that. That's sort of the basic intuition behind TAPIFN. And here's a toy example for how that intuition plays out with some toy data from scikit-learn. We have this, two moons data here, where we have like a little cluster of data here and another cluster here. And on the right here, we have the TAPIFN predictions. We also have, for example, cut boost predictions, which are very axis aligned, sort of unclear uncertainty estimates. But for TAPIFN, we clearly see away from the data, we become very uncertain. The white here is maximally uncertain. And yeah, so it's very smooth and well calibrated and sort of makes sense in terms of the prediction. And the cool thing here, and here is sort of maybe a provocative slide to the AutoML community that I helped to found. Our AutoML system, AutoSKlearn, is just very complex, and you don't need that complexity anymore. You don't need to have like a Bayesian optimization over a machine learning pipeline and meta learning and assembling and all kinds of code that runs for 48 hours. No, you just do a forward pass in a neural network, and that's all. And you could actually put this on a sensor, like you could write it out into Onyx and put it on a sensor, and then you have on a sensor a machine learning algorithm that can take new data sets and learn new classifiers. So it's not just a classifier on that sensor, but it's actually a new algorithm that is adaptable, and you could tell it new input data and it will learn different functions. And you can do that in a forward pass. It's pretty powerful and super portable. And quantitatively, and this is a result from 2022, actually better performance in 1 second than any other machine learning or AutoML method in 1 hour. This is comes with a lot of caveats. This is a result that's on average across 87 small numerical data sets, no missing values. And this is not true for every single one of these 87 data sets, but on average. The limitations were plentiful. So this was only up to 1,000 data points, up to 100 features, up to 10 classes, and didn't support categorical features, missing values, uninformative features, only classification, not regression, and had a very high inference time because, well, for every new test data point, you would actually take the entire data, put it into the context, and also put the new data point and do a forward pass through your expensive neural network, where in XGBoost, you just trickle down the trees, and that's much faster than doing a forward pass through a relatively big network. So lots of limitations, not something that data scientists would want because like no real data science problem has all these, well, you always have some of these characteristics, not always, almost always, but this wasn't a real product. But it was really promising. Like you could get like 36,000 times speedups. Like from an hour to here 0.1 second if you're on a GPU, 1 second if you're on a CPU. So it's still 3,600-fold speed up and just doing a forward pass. Kind of cool. So because of that, we then said, okay, let's build this for real. Let's solve all these problems. And that's what we did in TAPIFN v2. We actually resolved a lot of these limitations. So we went to 10,000 data points, into 500 features, and also supported categorical features, missing values, uninformative features, also supported regression, and put in a KV cache in order to reduce the inference time. The results were sort of still similar. Now we take 5 seconds, not 1 second, and the other methods take 4 hours because it's just in general like larger data, but the same result holds for this larger data. What did we do going from V1 to V2 more precisely? So we changed the attention mechanism to support more data points, course, also put flash attention and things like that. So what the deep learning community has built in the meantime, and that's kind of nice, the deep learning community keeps building, and just TAPIFN keeps getting better because we get better and better tools from the community. So that's it's nice to sit on the shoulders of giants there. We also changed the architecture to support an arbitrary number of features. So it's designed up to 500 features, but you can also put 501 or you can put 1,000. It's not going to break. It's just not that the prior isn't really made for it, but it's not syntactically impossible. Whereas over the previous method, you could not put 101 features. It's not possible. It would just, if you have less features, it was padding up to 100, and then that was it. And the new one, it's just indifferent. It's just doing attention and is meant to get 500 features. But if it gets 1,000, then it gets 1,000. And most of the improvements were in the prior. So we put a lot of effort into like really making categoricals full citizens, to put trees in the structural causal model, to have different activation functions like sine and logs and exponentials and so on, discretizing categoricals directly in the prior, lots of engineering. And we also demonstrated some foundation model capabilities that I'll talk about later. The new architecture, again, we have here this X-train, Y-train, X-test, and question mark. And the question mark is what we're predicting for. So the new architecture, we do this attention across the features. And the test, the Y, is just like one part of this. And then attention across the samples. And we do this across many different layers. Well, and then there's an MLP to move to the next stage. Just like in standard attention, but so now we have this axial attention. So instead of one attention that is across all the elements in the context, we actually have one attention across the columns, one attention across the rows, and then followed by this MLP, and we do that 12 times. And then in the end, we read out the representation for this point here. We read that out of the MLP with another MLP to get this predictive distribution here. This predictive distribution, I don't actually have a slide on that, so I should clarify that here. We actually have a histogram distribution, so we can fit multimodal functions like here. Basically, what we do is we take the input data. So we take data from the prior, we push that through the architecture, look at where do the samples end up in terms of the logits, and call sort of the lowest half, for example, the negative class, and the other class, the positive class. But we also, so that's for classification, but for regression, we can also say, well, we just push the logits through, and we're gonna like bin like 1,000,000 samples from the prior into 10,000 bins, and the lowest 100 data points go into the lowest bin, then the next 100, the next 100, and this is adaptive. So if we have a lot of data points around one area that are very much within epsilon, then these 100 data points are in a very small bin. So that's what you see here. There's small bins that are peaked. And we can also have just very wide bins for sort of the outliers. All right, so that is the architecture. And so as such, if you have like 501 features, then well, there's 501 features here, and attention is just doesn't care, it length extrapolates. All right. The qualitative result here is that, yeah, it's very flexible and also strong uncertainty estimates. So one thing you can do that is interpolation. So for example, here we have a sine task. You get the sines where you interpolate, versus boosting methods would just have the piecewise constant predictions. And MLPs would have sort of ruggedy interpolations. But MLPs are also pretty bad at these jumps. That's where trees are amazing. They model this perfectly, and linear methods are horrible. MLPs are also pretty bad at this. And for a neural network, we can model the jumps quite well. Not perfect, but okay. We can model noise. So if we have noise like this and a hole, then we'll predict in here with some uncertainty, and that is well calibrated. And if this noise grows over time, then actually our predictions also grow over time. So modeling heteroscedastic noise is very easy with this. Having worked in Gaussian processes for hyperparameter optimization, this type of heteroscedastic noise was a major pain before. Because you often have this heteroscedastic noise, for example, in optimizing hyperparameters of your neural networks. If you make the learning rate too small, then it's just, well, your noise is going down, but it's just super slow. If you make it too high, the noise is getting higher. If you make it just at the critical value, the noise is actually very high, because if you go a little bit to the side, then it explodes and you get really bad performance. So that's one example of from hyperparameter optimization, where you have this highly heteroscedastic noise, and modeling it in a Gaussian process is really annoying. So there are these ways of doing it, but that's a pretty complex piece on top of a Gaussian process. In a PFN, all you need to say in the prior, well, some of the, this noise is actually a function of some of the features. And then you get this. And all of the modeling framework is exactly the same. So it's just sort of a 1 or 2 line change in the prior. And that makes it pretty powerful and very adaptable to actually adapt to all kinds of new situations. All right. Yeah, we can now fit these multimodal predictions. This was a Nature paper, so we thought we need to do something very scientific. So we did this double slit experiment from physics, basically data from there that shows a wave particle duality of light. So when you have like a small slit in the, like black, and then a small slit and light goes through, then you see this interference pattern on the wall. And so you see, like, for example, like on the wall here, then you see it's bright, not bright, bright, not bright, brightest, not bright, bright, not bright, bright. And TAPFN can actually model that quite well with 5 different modes, and CatBoost can model it as nicely. Quantitatively, yeah, the results are sort of as before. Again, as before, the improvements are not everywhere. There are data points where it's not as good as CatBoost, or some data sets where it's not as good, but by and large, for most data sets, it's much better. And yeah, you see here XGBoost, CatBoost, LightGBM, in dark blue, the default, in light blue, the tuned version for 4 hours. So if you have like 4 hours of tuning and like 5 seconds in forward prop in TAPFN was much better on average. For regression, the results are somewhat similar, but not quite as good in V2. In V2.5, we pushed harder here. But yeah, there were a couple more data sets here where CatBoost was better. But by and large, still with a forward pass better than the tuned models on average. All right, in terms of ablations, TAPFN 2 was then robust against uninformative features. TAPFN 1 was totally not. TAPFN 1 was much more like this MLP. MLPs really hate uninformative features. The performance completely drops from like 0.6 to 0.2, like worse than linear models. They just can't handle this very well in overfit. And TAPFN 1 also didn't work well there. And in TAPFN 2, again, in the prior, we told the prior, there might be some uninformative values, which in the causal graph means there's just these variables that are not connected to your y at all. And as such, you should just ignore them. And so it just learns, well, that this might happen, and it just can ignore them and not care so much. Likewise, missing values. Previously, missing values were a problem, where you just couldn't handle them at all. And now, yeah, in the prior, we say there might be some values that are missing, and then the model just learns to deal with that. Categorical features, again, we focused on in the prior a lot, and that works well now. And then, yeah, this result I mentioned with less data. So with like 50% of the data here, WFN is as good as CatBoost with 100% of the data. And with 25%, it's as good as 50% of the data for CatBoost. All right. I did mention these foundation model capabilities, and I'm pretty excited about these because you can fine-tune this WFN to your own tabular data sets. So just like you can fine-tune an LLM, you can download a llama and fine-tune it to your text. You can download a WFN and fine-tune it to your types of data sets. And here's a toy example from the Nature paper. So in yellow, we have the true function, which is actually just a sign function. And WFN doesn't know that this is a sign function, just sees these orange data points and fits a model to these. And the model is okay, but not great. For example, here it just goes off the function, and here it goes a lot off the function. And if you see the same orange data points, but you have fine-tuned your WFN on a couple of sinusoidal functions, then sinusoidal functions become much more what the WFN thinks it's going to get. And the predictions are dramatically better. It's not perfect, right? It's still off here a little bit, but so it's not it doesn't do functional approximation. It doesn't output the formula, but it outputs just the predictions, and they get much better if you fine-tune it on similar functions. And you can also fine-tune on sort of broader sets of data sets, and we also did that. In real WFN, we actually fine-tuned to some real data to, like 40 different data sets, and then we evaluated on other data sets that are not overlapping. And there we actually see that, you can still get the significant improvements over the WFN that was only trained on the synthetic data. All right, there's some other foundation model capabilities. So you can use this for density estimation. So if you have some data and you just want to say, well, what's the density of my data, then you can cast that as a tabular prediction task, basically call the WFN many times, call it basically for the probability of the x value being a certain value, and for the x2 given the x1, and for the x3 given the x1 and 2, and so on. You can do data generation in the same manner. So if you have some actual samples, so this is now the synthetic data generation that I mentioned before that many other companies do. When you have some actual samples here in blue, there's a lot underneath this yellow patch, and then you generate yellow data points like the ones, then you can generate data with very similar properties. And the retrieval, you can look at the embeddings of WFN, and they're very meaningful, much better than the original data embeddings. All right. Then 2 months ago, we released WFN 2.5. That scales up further and clearly outperforms WFN v2. And basically, we trained more. We now train on H100s and not on RTX 2080s anymore. The whole Nature paper was on RTX 2080s, which are these 6-year-old gaming cards. And the final model was trained for 2 weeks on one of these nodes with 8 RTX 2080s. We did have a cluster of 200 of them lying around, which is super helpful in order to do all the experiments and so on. But the final model could actually be trained in 2 weeks on one of these nodes, which is, GPT-1 scale maybe. And by now, we were training on H100s, and we train on bigger data and for longer and so on. And that is the biggest difference in v2.5. And it does get better on this internal benchmark where we can run WFN v2. And it also scales to now 100,000 data points. So this is a live leaderboard on Tab Arena, which is a data benchmark of data sets that go up to 100,000 data points. And real WFN is also the best model on this one. All right. What we also released in WFN 2.5 is this distillation engine. I mentioned the slow inference before, and that we have a KV cache in V2, but the KV cache has its problems. It's also not super fast. So what you can do is actually put a distillation layer on top of the neural network and basically approximate the the TAPFN predictions with an MLP, or actually we also have a tree approximation that is very, very similar in terms of performance to this MLP. So if you, for example, are in a regulated business, in a bank, and you have been serving trees for the last 20 years and you want to continue serving trees because then you don't need to go through regulatory approval anymore, then we can just distill the TAPFN into a tree, or into a tree ensemble, and it works better than native trees. Because if you have a small data set, then TAPFN gives you something that generalizes well, whereas the trees overfit. But then in order to approximate the TAPFN, you can generate arbitrary amounts of data and see what would the TAPFN predict. Let's predict that with a tree. So you have infinite training data in order to basically approximate the tree, the TAPFN. And so you don't overfit on that anymore. All right, then we also have scaling mode that now actually wraps around this model and basically does some type of retrieval to put the right data points into the context, and that allows you to scale to like 1 million or 10 million data points. And so that is a scaling like by 1,000-fold since the Nature paper, which is kind of cool. All right. That wraps up TAPFN 2 and 2.5. And next, I would just like to briefly talk about some time series. The rest of the talk is actually much shorter than so far. All right, time series. I showed you an exemplary time series before. This is a univariate time series where you have one signal over time. And what you can do is actually collect features from this. So you can say something like the running index of each of the data points, the year, the day of the week, and so on at this point, and create features like that. And as a y-value, just say how high is this time series. So that's a y-value here. And you can also compute these features for the future. And then you have your x-train, y-train, x-test, and you can feed that into TAPFN to predict the question mark, which is the y-test. And this really simple method actually achieved the state-of-the-art on the most popular time series forecasting benchmark GIFT-eval last year in January. Doing better than much larger models by Amazon and Google, despite the fact that we used for this exactly the nature checkpoint, a checkpoint that was only trained on synthetic tabular data, checkpoint that had never seen a time series in its life. It's never seen this encoding of time series in its life, and it's never seen a real data set in the first place. And this compares to all the other methods who have seen synthetic data and real data from time series. And but in the meantime, of course, there have been a lot more time series forecasting models, and it's very clear you can do a much better job by pre-training and fine-tuning on time series. And of course, we're also looking into that a lot more now. Right, that was all for time series. Interpretability. I mentioned this result before, that the predictions actually seem a lot smoother and better calibrated than with boosting. So with boosting, we have these weird parts of the uncertainty bars where we're like, well, I don't know why the model is uncertain about this part, or why it's more certain about this part here than about these other two parts. And this sort of ruggedness in the predictions actually also leads to post hoc explanations on top of trees being a lot more rugged than post hoc explanations based on top of TAPFN. So with TAPFN, we have very smooth predictions. And then if we, for example, run SHAP and look at here, what are the predictions for, this is an example for credit rating. We have two classes. The blue class is customers that have an account already, in the red class, customers that don't have an account. We see that with age, you become more creditworthy. But if you have an account already, that's a red class, then that effect isn't quite as big. We can kind of see that from this plot. And from this plot, knowing the pattern, you can maybe also figure this out, but it just seems a lot less interpretable. And there are actually some theoretical results where boosting algorithms can be arbitrarily bad in terms of sharp predictions. So they can be very misleading if you have these very sudden jumps where the gradient in your predictions is basically infinite. That can really screw up sharp values. And with SubPFN, we have very smooth predictions, so that that theory doesn't apply there, that you can get arbitrarily bad results. You can also do other things like actually on top of a TabPFN, actually basically have a hypernetwork that outputs the weights of a neural network so that you get fast predictions, or not the weights of a neural network, but actually a generalized additive model, as in this figure here, where a generalized additive model basically just looks at each of the features and gives you a shape function with respect to that, like here. So here's a ground truth function as an example that just says, like minus x1 plus nothing. So x2 is completely irrelevant, plus x3. And then see whether that's larger or smaller than 0. And then if you look at the shape functions, you basically get this minus x1. X2 is irrelevant if you look at the shape here. It's up to 0.25. This is up to 20. So this is basically 0. And this is plus x2, plus x3. So the predictions are very, like, basically from these shape functions that are the direct outputs of the GAM. You can directly understand what this model is doing, and you can say, well, if my customer would have a different value of x1 that's a bit higher, then they would fall into this in this class. So that makes it very interpretable. And the blue method here is EBMs, that's explainable boosting machines. It's basically another way of outputting a GAM. And so this GAM former actually does a forward pass in order to output a GAM. So it's a different way of training a GAM, basically. But the output is exactly the same shape or the same type as an EBM would output. But now you can actually get this in a forward pass of a foundation model, which is kind of nice. The accuracy here is worse than TabPFN, but it's actually still on par with XGBoost, so still quite nice. And then on to novel capabilities. So we also looked at robustness to data drift in TabPFN, which is drift resilient TabPFN, where we basically said, where we modeled drift in the data, and we basically had another dimension that is this C column, which is sort of your time or the drift strength from your initial distribution. And so if we have seen as a train domain 0 to 3 and then as test domain 4, 5, 6, we actually see this blue class is moving through these other classes, and the predictive distribution is actually moving with it. Whereas in the original TabPFN, it would just directly make a lot of predictive errors by not modeling this. And so you can model out a distribution. And this is done by basically in the prior having some of the edges modulated by time and actually changing over time. Kind of out there, but you can do really cool things with this, namely counterfactual fairness. So the counterfactual reasoning is basically asking the question, what would the result be if a protected attribute would be changed? So if, for example, a patient is male rather than female, then we want to not use this gender or sex in order to make the predictions, but you can't just naively only take out that feature because there's a lot of correlates of that feature. For example, the weight and the height and so on. From that, you can tell with high probability whether a person is male or female. And then, so really you would want to remove the causal effects of this protected feature on the other features and basically take that out of the data and make a prediction with that effect taken out. And that is very elusive normally, but in TabPFN, you can actually do this because in the prior data sets, that like those are entirely under our design. And so we can just say in our structural causal model that we use to train that sample once with this protected attribute here, that's A0, with the outgoing edges in. So we sample once, that gives us the biased training data. And then we sample again with these red edges cut. We get different, so we get fair values for the other x's, and then we also get the fair values for the y. And we know that all the data that we observe in the real world, well, that's just, you can't just go and change the gender of a person. But so like all the observational data is just, and you can't take out, okay, well, if you were male, then your size and would be this, etc. That's just very hard. So all the data that we have is biased, the training data, so the X train and the Y train, and also the X test. But then the Y test, that there we actually use the fair one. So basically we say from this biased data, we want to get the fair predictions. And since we can do this sort of in silico in our training data, we can generate hundreds of millions of these pairs of biased and fair predictions and learn from the biased X train, Y train, X test to predict the fair Y test. And this actually then was a new state of the art for counterfactual fairness, which is sort of the fairness notion that is closest to the law. Maybe a little easier to understand is sort of this interventional reasoning. That's also all about causality. So how does an operation affect the chances of survival, for example? So here we want to predict the distribution of Y, our target, after an intervention T. And this is this do calculus, where we do make this interaction, we decide to have this operation. And we can't just say, well, let's look at all the data, observational data where the operation was done in the past, because there's a reason that this operation was done. Well, the patient was sick and they had these symptoms. And so you can't just go and say, well, this is a life expectancy of the patient if I do have the operation, and this is if I don't, based on this observational data. But what you do need to do is have randomized control trials. Then you can do this, because then this here is replaced by do T equal T. That's what the randomized control trial does. We can't do these computations. We do need to do these computations on the right. And any normal machine learning method, XGBoost, CatBoost, also TabBFN, would do the prediction sort of on the left. So you do need to change something in order to get to the right. And in the TabBFN framework, this is actually quite easy to do. Again, you take the SEMs, and for an SEM, you generate first the standard data. T is this interventional variable here. And so you generate, and the T has some inputs, right? There's a reason that the operation is being done. And then you generate this data again, but cut the inputs here and rather have this do operator and set the value. And then basically from this observational data, you take the interventional data for test and predict the interventional Y value. And so you can then learn to predict the interventional Y, and this actually does do a lot better than, well, the standard method. So because, yeah, random forest, TabBFN, etc. are entirely biased there. And it also is actually better than other traditional causal ML models. And then we also applied TabBFN 2.5 for that. So there are frameworks that do transfer a standard base learner into a causal learner. This is called double machine learning. And so there's 3 different methods: this X learner, an S learner, and a T learner. And this here is sort of a, kind of AutoML method, not one that we designed. but sort of that is the state of the art you could get with sort of XGBoost, etc. And then the XLearner with TAPIFN 2 and with TAPIFN 2.5, it just keeps on getting better. The T-Learner happens to be the best. And then when you actually compare that to other causal machine learning models, then you get very strong predictions and yeah, get the new state of the art in causal interventional reasoning. All right. With that, I would get to exemplary use cases. Conscious of time, it's sort of been an hour. Do we want to do some questions now, or like actually like probably 5 more slides, a demo?
You can continue if you want.
Yeah, let's do the slides and then maybe have questions. All right. Yeah, so there's all kinds of different things we can do: classification, regression, forecasting, anomaly detection, data generation, multi-table reasoning, fine-tuning, text integration, causal reasoning, interpretability, and applications are sort of in all kinds of different areas here. And within one of these areas, there's many different applications, thousands of use cases, things like customer lifetime value prediction, load forecasting, predictive maintenance, etc. But let's talk about some details. So Boston Gene, for example, used TAPIF, and actually I think they used V1 already. I think this is an old result where they happen to only have numerical data for this particular paper, but they actually got a 53% error reduction. They could do 10 times more work, and actually allowed them to focus on meaningful clinical analysis rather than sort of doing the hyperparameter optimization, etc. Then we have a collaboration with OxCan, Oxford Cancer Analytics, where we predict doing early detection of lung disease. And of course, that would allow us to save more lives. This is an ongoing collaboration with a customer. Hitachi is a customer where we predict defects in rail tracks. This is, of course, the recent accidents definitely suggest why this is important to do. And we've just started, and hopefully we will be able to detect defects better and challenge, improve the maintenance, etc., and focus the maintenance on the right parts of the tracks, etc. And then, we also have use cases with here a bank whose name we can't disclose yet, where we forecast portfolio growth to optimize treasury liquidity planning. But in general, this bank is just very interested in replacing all kinds of different bespoke models across the company with just one model that just allows to have this foundation model interface where you don't have this model that some intern built 3 years ago and you don't know where the data was anymore and where what the assumptions were, etc. But you rather just have the data, you feed it into a ChatGPT-like interface and get the right predictions out. So that's sort of the value proposition of tabular foundation models. And then I just would have a collab demo, but maybe let me wrap up first. So takeaways are tabular foundation models are the new state of the art for small tabular ML. Natively is scaled to 100,000 data points and 2,000 features. We have the scaling mode that lets us scale further, but we haven't fielded that sort of as a product. We have that in-house. So if people want to send us data, we can run on that. The unique features compared to previous methods are that it's faster, no HPO, etc. Just very interactive data science, better peak performance, and works well with less data. You can do fine-tuning. And PFNs also enable this counterfactual and interventional reasoning and allow you proper what-if analyses, which is super important because in practice, you don't just want to make predictions in order to make predictions, but you actually want to act on your predictions, and then that becomes interventional reasoning. And so I'm super excited about this direction, where we're also working with Bernhard Schulkopf, and very excited about that part. All right, with that, let me pause here and take questions. Thank you.
Fantastic. Thank you. Thank you very much, Frank. This is fantastic. Really nice talk. We have quite a few people wanting to ask, and I think I'm going to go first with Paco, that I believe he wanted to ask you as well. I think, yeah.
Thank you. Thank you. Thank you very much, Frank, by your very interesting talk, and congratulations by really is fantastic, the model and the performance. I have a question about the high imbalance data set, when the imbalance is very high, and then it is necessary to introduce different pre-processing in order to detect really the positive class, the very small class. Have you been thinking about that? How to readapt TAP PFN for this kind of problems?
Yeah, so the short answer is it doesn't seem to be a problem, but you do need to do your calibration right. So, and if you, for example, optimize for accuracy, then and you have this, I don't know, 1% minority class, then yeah, by predicting everything is the majority class, you get 99% accuracy, and that's of course not what you want. So you need to then look at balance accuracy and do a calibration of your probabilities. So this post-hoc calibration is it's a super quick step, but if you don't do it, and TAPFN can do it automatically if you tell it to, then that works. But that requires like to tell it the metric that you care about, and that metric shouldn't be accuracy, but balance accuracy, for example, and then it actually works off the shelf. Why? Because in the prior we said, well, there might be imbalance, and so it has seen imbalance data before and can actually predict well for it. One thing we haven't done yet, for example, is you could say you have 100 million customers and only like 1,000 of them are in this class, so like super crazy imbalance. There I would expect at some point, you know, it's a bit out of distribution. But this to get like this really extreme imbalance, you also get beyond the 100,000 data point limit. And then we would need to also look at that with different architectures for the majority class.
Okay. Thank you very much. Congratulations by the talk.
Thank you.
Thank you, Paco. So I'm going to go in order what I've seen in the chat. So we've got the question from Carlos asking you in the chat if you tried before using deep learning embeddings as tabular data, and so like image features extracted from some CNNs type of thing.
Yeah, so we haven't worked with images ourselves much. Others have. There are published papers on PFNs, on also directly TAPFN based on image features. We have some work on text embeddings, and there it works really well. You don't want to put like, I don't know, 512 dimensional text embeddings in as 512 new features. But you can, for example, do PCA and then have like 30 features and throw those in, and it works beautifully. You can also do TF-IDF encodings. Yeah, we actually have a paper under submission on that. That works extremely well, and actually better than other models that are specifically for multimodal data like context tab or tabstar.
You only need to tell us what you're not doing, so we can try, right? All right, so Ramila, I think you have a question. I don't know if you have your microphone, if you want to directly ask yourself, or I can read it out.
Yeah, so the question is for...
Yeah.
Go ahead.
Thank you. Thank you. Great presentation. I was curious because since this is a relatively newer technique, and it's not obviously discussed or covered in some of the more quant finance classes, what are your thoughts in terms of how it's perceived within the financial community or the quant finance community in terms of application? Get any thoughts there? Thank you.
Yeah, very good question. We did get a lot of interest from quants, so definitely it has come up. several different answers. So like the finance community in general, there's a lot of parts in finance. There's, credit risk, there's lending, there's insurance, etc. Some of the data sets, they're very large, like 10 million, 100 million data points and so on. Others are maybe 100,000, and we definitely have customers that have in the lower range, and that find our models to outperform the pipelines that they have tuned for the last couple of years. If it's more in the millions, then we would have to use scaling mode, which we only have in-house so far. For quants in particular, there's different types of quants. If you want to do high frequency trading, where you want to have like sub-second or sub-millisecond predictions, then inference is currently too slow. And yeah, that's not really where TabPFN would shine. If you're more in the bond trading or the multi-day predictions and you trade once a day or something like that, then you can get very good performance out of it. In general, the priors of TabPFN that we use have not focused on signal-to-noise ratios that are as low as in quant trading. But yeah, that's just because we haven't tried. I think we could make a model quite easily that is better for low signal-to-noise ratio, and that would probably then improve further for those types of cases. Any further questions along those lines, or did that cover it?
That's great. Thank you.
Thanks. And yeah, like of course, yeah, we're looking at being like reducing the inference costs and scaling to larger data sets, and that will broaden the use cases. And I mean, so far from TabPFN 1 to 2, we got an order of magnitude improvement, like order of magnitude larger in state of the art, from 2 to 2.5 again, and with 3 we're also aiming for that. So we're aiming for 1 million and also a faster inference.
Great. All right, more questions. We've got Israel there. If you are there and with your microphone, you want to ask away. Otherwise, I will read it out for anyone on YouTube as well.
Yeah, this is not a bad question at all.
Okay.
I don't. Do you want to ask it, or should I raise it?
If you just go for it. I mean, you've read it, right? So just simply.
Yeah, maybe we will read it for the YouTube record, but if you want.
Yeah, so I don't really know if this can be a silly question, but I'm an LLM person, so I would like to know if it's possible to make some kind of prompt tuning using TabPFN, like just introducing some few tabular examples of your specific domain, and without any fine-tuning, to then observe if that improves the prediction performance of the pre-training model without changing any weight, neither introducing any additional layers. So there is prompt tuning. Maybe just to make doubly clear, since you say without changing any weights, none of the TabPFN inference does change any weights. So it's always just the forward pass. It's always just in context learning. But it is a very good question. What do you put into the context? So if you have 1 million data points, then it becomes a very relevant question what you put into the context if the TabPFN only is meant to accept like 50,000 or 100,000 elements in the context. And then this is very much a question of prompt tuning. And so, yeah, we have scaling mode, which is, of course, doing something along these lines. But so there's different things. There's retrieval, which picks the right elements to put into the context, and then there's actually also soft prompt tuning, and we do have a published NeurIPS paper on that. You can do that, and it is very helpful as well.
All right. Well, if you allow me, I'd like actually to follow up on that one because my question was, well, I have a couple of questions that are quite similar. So let's say I have, you did say that fine-tuning is something that you can do to TAP-PFN, right? And so I was wondering if I have a relatively small data set, I just want to apply TAP-PFN to. And do you think it makes sense to do any attempt to fine-tuning, or just simply use it as in context? Just tell me what to do. What is your advice there, or some prior from my own side, just generating data? I don't know what your thoughts are on that.
Yeah. So if you have one small data set, just put it into the context and do a forward pass.
Yeah, that's it.
It's very, very clear. If you have 2, 3, 4, 5, 1,000 similar small data sets, then you would want to meta learning cross them and sort of adapt your TAP-PFN to that type of data. And then you will get better performance in each of these individual small data cases. But
so would you suggest that I generate artificially something similar to my data and keep fine-tuning TAP-PFN, or would that be a bad choice?
That is a very interesting question, and we actually have a workshop paper at the Europe's workshop on AI for tabular data that does precisely that. So it takes a small data set and then actually generates a prior that is resembles that tabular data sets and samples from that and fine-tunes on that, and then actually runs it, and it does improve. But it is a bit more complex.
Yeah. On the same line of, let's say, foreseeing how TAP-PFN works, I've seen TAP-PFN being used like a few-shot learner, right? So just trying to give it a very small data set with a few labels, and it seems to work in general. You said 50%, right? But there are people using it with 2% and 5% of the data, and it seems to work. But I guess in the way you've done the prior, from what you explained, it's not ready for that kind of few-shot learning classification regression type of thing. So I was wondering if you think we could do a version of few-shot TAP-PFN, if that makes any sense, or if it's not necessary at all, maybe.
Yeah, it does make sense. So it connects to one of the limitations of the public versions of TAP-PFN is that it's actually, it has the same interface as XGBoost and scikit-learn interface, which, for example, does not include the column headers. So it just doesn't care what the column actually is. And if you have a small data set with like 2 data points, and you do want to know what these say and what the columns are, and you actually want to ask an LLM, like, do the contextual reasoning, you're not going to do statistical reasoning with the 2 data points. That's not going to be helpful. So there's a sweet spot up to like 10, 15 data points. Actually, the contextual reasoning is more important. There's, for example, this Tabular 8b work that fine-tuned the llama in order to do this. And that is better up to 16 data points, but then quickly it doesn't work anymore. So it can't do statistical reasoning very well. That's what the LLMs are bad at. But the contextual reasoning LLMs are fantastic, right? We all know that. And it is something that we're working on to get the best of both worlds, the contextual and the statistical reasoning. And so we actually in a European project, the Elliot project, multimodal foundation models, and there one of the goals is to actually do a joint fine-tuning of tabular models and language models and so on, in order to align the embeddings, and then you can actually get the best of both worlds.
Great, thank you. We still have plenty of questions. If you're happy to take more, and I'm happy to. Yeah. So we've got Mario Alfonso. If you want to go with your question, please. Mario, you're muted. There you go.
Yes, I just wanted to ask, because you need to generate data sets that are, you have been saying, resemble the statistics on, let's say, real-world data sets, because the statistics of real-world data sets are very different one to each other. Have you experienced like some kind of field drift or something like that, where in a specific fields it doesn't work anymore at all because it's not similar, or do you find that with enough complexity in your data, in the trained data, you can achieve to work on, let's say, any kind of statistics?
Yeah, so it's really the broader your prior is, the more you will cover. Maybe think of one example. If your prior is basically linear functions, so you say my relationship is always a linear function that you sample in your prior, then TABFN will provably approximate Bayesian linear regression. But if you have a quadratic relationship, it will just not cover it, and you can make completely adversarial cases where it will perform arbitrarily poorly, and that sort of suggests that if you are in a domain that is sort of outside of the possible data distribution that we looked at, then you can get horrible failure modes. And as a corollary of that, we actually made our prior distribution sort of as broad as possible in order to cover as much ground as we can. And we haven't seen a lot of adversarial cases yet. There was this question about trading. So low signal to noise ratio might be something that, well, we're clearly putting in now. Into the next versions, because that might not be as well covered. Like it does look for some signal, and if there's just no signal to be had at all, or just super low signal, then it might not handle that as well. I mean, it does all right, but I think it can do better there. But in general, we put out this one model, and this one checkpoint is being used across thousands of different use cases. So it is surprisingly robust.
Thank you. So next in line is Oroel. Please go ahead.
Hi. I'm Oroel, working in industry under the supervision of Professor Isaac. And my field of research is self-supervised learning, but in the same time, I have been closely following the development of PFN and your personal work, Frank. So I'm curious about your thoughts on prior fitted networks trained with some self-supervised learning task in order to get some kind of task agnostic representation from tabular data. I'm thinking bioinformatic fields applications where it's common not to have a label on your data.
Yeah.
I have found NeurIPS this last year. Some models called Theus based on TabPFM versus one. I don't know if you are familiar with that
Theus,
one.
actually, I don't think.
Theus sought embedding for unsupervised separation. It's basically a modified version of TabPFM versus one, designed to cluster the data, enabling the context. But
yeah,
I don't know
I actually also saw something that looked like an ICML submission on Archive the other day that was all on cluster PFN. But yeah, I think by all means, I mean, you can already take the embeddings of TabPFN, and they're helpful for clustering. But if you optimize more along these lines, and then you take data that doesn't have any, like if you take data from that field where, so the simplest thing you could do is to just take data and sort of punch holes and then call a column your Y column and predict that from the other columns. You could also, generate arbitrary amounts of data sets like that, like from one X matrix, just take one column as the target and a random subset of the other ones as features. That's what TabDBT, for example, did. And I have a paper with the TabDBT authors at the Europe's workshop again, where we showed that you can actually get a meaningful in-context learning from just a single data set. If the single data set is, for example, has 100 features, then you can generate 100 training data sets from that, where it's like one feature at a time is the Y and the others are the X, and you can generate infinite numbers if you take subsamples. Well, not infinite, probably like 100 factorial de facto infinite from this one data set to train on, and that actually gives you pretty strong in context learning performance, sort of above the level of a random forest. From a single data set, which is already very surprising. And then if you have more data sets with the right characteristics from clustering, yeah, I think you could build a good clustering method on that.
Thank you very much.
Thank you, Roel. More questions. Michelle, I'm hoping I'm pronouncing your name correctly. Question about the data generation, the synthetic data generation. I don't know if you're there. Yeah, there you go. You're muted for now. While she finds it, and you can start reading it if you want.
Yeah, so the question is about synthetic data generation and whether you can, what constraints can be applied during the generation. So this is really just, you would basically just say, well, this is my data. For example, take, there's a cold start problem, but basically say I have no features and my X1 is my target, predict the X1. So it's going to predict something that is like the X1. It's basically going to sample more or less from your distribution of X1. Then it's going to take that X1 and say, this is my X1 data, this is my X2 data, X2 is now the Y, so it predicts X2 given X1. And you sample X1, so then you're going to sample X2 given X1, then you sample X3 given X1, X2, and so on. So you sample forward, and you can just sample as many samples as you want. And each of these tries to mimic the predictive distribution of Xi given X1 to Xi minus 1. And as such, it just tries to mimic the constraints that are there in the data. There are no precise constraints. So you can't say X3 has to be bigger than X2 or something. If you want that, then you could just filter the data, for example, and do rejection sampling. But that would be the short response. Is that a good answer? I see you're nodding, but if you have any follow-up questions, please go ahead. Thank you.
Great. Alberto, there you go. Unmute yourself, please.
Can you hear me? Hi.
Yeah. Yes.
Okay, thanks, Frank, for your time. Just something I didn't really get. You talk about concept drift in your prior, and you said something about introducing a notion of time in your causal models. Is it right?
Yeah. So basically, this was a one slide on drift resilient TAPFN. So there we basically had in our SCMs, we would basically have sort of the second order SCM that would modulate how the connections in the SCM change over time. So then we could sample data from the SCM, and then we could say, okay, now there is a change point, and some of these connections are changed in various ways. For example, one connection gets weaker, one connection gets stronger, one connection gets more quadratic or whatnot, and model how that might evolve over time. And then, from data from, say, 3 time steps, you can predict what's going to happen in the 4th, 5th, 6th as time flows forward. That is one instantiation of that. There's a lot of different ways one could do that, and I think there's a lot to be done there.
So you don't have for a certain data set, when you're generating one data set, you don't have one causal model, you have a couple of them that interact over time. Is it right?
So for one, so during the generation of the training data for this drift resilient TAPFN, we would have one SCM, and then there would be some variables that act on some of the nodes or some of the connections rather in that SCM. So you would have sort of this meta thing that modulates the SCM and changes it over time.
And that's completely controlled by you, right? changes that it makes?
Yeah, it's just, well, it's a synthetic generated way of modulating it. And if you, for example, have domain knowledge of how it should be modulated, then that could be coded in.
Okay, thank you. Thanks.
Thank you, Alberto. So we also have a question from Adriel that I think is very similar to my question, but more like guessing if you can anticipate what to do.
I am here. Oh.
Yeah, maybe go with Mario. And yeah, this funny situation, Frank, that some of them are at the student residency, so they are all together in one room, but that's all we could do today. That was really...
All right.
Okay, there you go. There you go.
Okay, can you hear me?
A bit low, but fine.
Perhaps I can get closer to the mic.
Yeah.
First of all, thank you for your talk. It was really interesting, also for my own field of research. So my question is mainly about how can you anticipate whether you need to fine-tune the model without observing new data? I guess this should be connected somehow to the uncertainty in the predictions, but I'm not pretty sure. So what are your thoughts about that?
So I think if you have a single data set and it fits into the context, my short answer would be don't fine-tune. If you have, well, there could be cases if you have sort of a large amount of data and it just fits into the context, and you could like take some of it to fine-tune and put the other part into the context. But by and large, I would say in context learning is incredibly powerful by itself, and especially if you care about predictive distributions and being calibrated and so on. And the more you fine-tune, the more you might actually overfit. And ICL as such, the training objective was not to overfit, whereas for fine-tuning, the training objective is sort of cross-validation, not overfit, but what it does in test, let's see.
Okay, yeah. Actually, I had like a three-part question. But I will make the second one, but very quickly. It's kind of related because that example of the sinusoidal function just triggered a lot of questions in my mind. Mm-hmm. So the second question would be, how could you select that data for the fine-tuning in case it is needed? For example, for that specific case of the sinusoidal data, your observations are not quite well distributed, definitely below the Nyquist frequency. So there is a lot of epistemic uncertainty around the actual generative function that produces those observations. So how would you create that data without?
So I would say again.
Yeah, how to produce your.
Sorry, I didn't mean like ask the question again. I meant again. I would give a similar answer to as before. If you have a small data set and fits into context, don't fine-tune unless you have extra information that is not in the data. For example, in this case here, it was like this data comes from a sinusoidal. Like the data doesn't tell you that it comes from a sinusoidal. But then if you know it comes from a sinusoidal, well, then fine-tune on some sinusoidal and it's going to be much better. If you know, I don't know, you have a physics informed neural network as a baseline, and TAPFN doesn't learn anything about the physics because it's not in the data, then yeah, maybe you can generate some data that actually abides by the physical functions that you know have to hold true, and then fine-tune on those, and then it's going to get better. So like anything that you know that's not in your data, try to tell it through fine-tuning.
And perhaps you're introducing additional biases, right? Additional priors, so to speak, to fine-tune. So you are introducing, for example, in this case, you're introducing a family of functions, the sinusoidal data. How this could contribute to catastrophic forgetting if you fine-tune with this?
Yeah, absolutely. If you fine-tune on sinusoidals and then test on other stuff, it will get worse. We have not tested how much worse, but I mean, we have fine-tuned on generic, on just a broad set of data sets, and tested on other broad sets of data sets, and it got better. So there it didn't have catastrophic forgetting. But if you were like you fine-tuned to one data set, at some point it's going to get worse on the other data sets very clearly.
Okay, thank you so much. I will try this model actually.
Cool. Thank you.
Thank you. So we have one last question to wrap up. I think Christina, I'm not sure if she is in the same room.
Hey.
No? Okay. Hi, Christina.
Hello. Thank you very much for the presentation. Just to introduce myself briefly, I'm also a PhD student of ISAC and working on self-supervised learning. So I actually applied TAPFN in one of my projects, but as a part, not as a standalone library, but as autogluon library, and it actually works really well with medical data. And I'm interested in whether the TAPFN would be working well also with genetical data, because as you know, they are characterized by being very sparse with a lot of zeros. And also we have the case where the number of features is like a magnitude more than the number of samples.
Mm-hmm. Yeah, very good question. We do have some collaborations with biomedical folks, RNA, and etc. One of my former students, now professor herself, Katharina Eggensberger, she did this TAPFN wide, where they did continued pre-training on a new prior that featured very wide data. We also have a follow-up work that looks on pre-processing and feature filtering, sort of inside of the network. That is not released yet, so I think the best thing that is released is a TAPFN wide. I would try that. And yeah, we're also looking at training models for both just many features per se, but then also more features than data points, because the short fat data is something that's very, very common in some applications. Granted, not that many, but and sort of pretty much all in biomedical.
Yeah, right. So just to apply out of the box, the TAPFN would not be working. I mean, because the priors are very different, so you would suggest to do maybe a lot of fine-tuning, or?
I would suggest trying it. I mean, trying it is super quick, but limit the expectations. Next, I would probably try TAPFN wide. That is also a release checkpoint. And so TAPFN, I think mine is wide like broad. And that was made for this type of biomedical data. So I would expect that to work not too badly. It's fine-tuned version 2. They also wanted to fine-tune 2.5. I'm not sure if they've done it in the meantime. But so they keep on building on this, and they have collaborators from biomedical. So as such, I think probably their objectives are aligned with yours. So maybe look at what they're doing.
Okay, thank you very much.
Thank you.
All right, fantastic. I think we are done with questions. So if you still want to show us a little bit of your demo that you mentioned before.
Okay, let me do so. So this is, let me move the Zoom bar somewhere. So if you Google TAPFN, you will find a GitHub repo as a first hit, hopefully. You can click there and then go down to Open in Colab as interactive demo notebook. This is where I am. I'm in this version here where I have already run it in the interest of time. But I'll just walk through and show you what there is. And maybe, that is just super briefly walk through. So first, as always in a Colab, so you have to run it. You have to run the first cell, run anyways. And Sorry, you have to run this cell. Click the wrong cell. And that does some installation, pip install, etc. And then afterwards, you need to remember to restart the runtime. That's always the case with collabs. So you go runtime, restart session, and run all, for example. And then it runs and does some simple imports. Import. Then yeah, it does some setup. And now let me actually switch over here. And then actually, yeah, so we just the new model of 2.5 that is on Hugging Face. So you need to get it from Hugging Face, and you need to have a token for that, or you use the client. The client uses our API. If you don't have a GPU, I would recommend using the API. But please don't send us your private data, because then we have all kinds of pain having your private data around, and we don't want that. But for public data sets, for example, or stuff that you're going to publish, put that into the API. I have gone through the step here, but then there's classification with TabFN, so where you just load some standard data. There's alternative data sets. You split the data, you just run TabFN once. So this is the first time it actually loads the checkpoint and then runs. And you can compare to other classifiers. So there's TabFN, there's XGBoost, CutBoost, and you can plot. So there's ROC AOCs here. There's regression, Boston housing, so standard data sets like this, other data sets. Again, you do one regression, you compare to other type of regression methods with cross-validation. Then you can also handle text data. This is actually only in the API because this requires a language model. So yeah, we didn't want you to have to mess around with API keys. So it just uses our API key. So you only need an API key for us, and then we internally use some language models. But so that wouldn't work if you try it without the client. And here I actually did run local. But then there's unsupervised learning, so this data generation that runs very quickly. Outlier detection also runs quickly, so you just say, well, from this data, if you have to mention, if you have to find some outliers, it would be the orange ones. Then missing value imputation, model interpretability. So the sharp values, they take a while. So this took, what, 2 minutes here? But then, yeah, you have sharp values, embeddings, that's very quick, 2 seconds here. And so there's just a t-SNE visualization of the embeddings. Then feature selection, yeah, it just, well, selects the most important features. And then you can look at the decisions boundaries for classification, for example. So if you have this sort of weird data that's circular, it's a classic case for you want to feature engineer, sort of distance from the middle is the one feature you need, and then it's actually quite easy. But if you don't have that, then it can be challenging. And yeah, so this does show that it does some sort of feature engineering inside of the model. And yeah, XGBoost would have this very axis-aligned representation. Then sine curve fitting, so this interpolation that you get rather than the constant predictions, piecewise constant. The uncertainty is in here. So if you have this missing part here, it does have this heteroscedastic noise predictions. Then there's time series forecasting, and yeah, here it says, I think, make sure to restart the session before. So I don't know, it's a stupid collab. So I need to restart the session. I haven't run this part here yet. But, and then what do I do? Not run all. I don't want to run all. Runtime, run cell and below. Okay. I just did restart the session. Stupid. Restart the session. Yes. No. Runtime, run cell and below. Okay, I don't know. Otherwise errors will follow. well, they do follow. But then there's time series, which is actually the smallest part, but there's the initial time series and then sort of the predictive plots. Oh, and there's also causality. But no, actually causality might then work. I'll just run it from here. Below. Oh, come on, stupid thing. Yeah, Colab has its issues. Like local is much nicer.
Live demos are always like this, Frank.
Yeah, I know it's we are putting a little bit more love into improving this. This whole Colab situation is not perfect. It's nice for, you can directly follow and you can do the same things and you can make a copy and change and put your data sets in and so on. For that, it's great, but for live demos, it's sort of a little annoying. Right. Oh, I guess we're still in time series. That's why. No, we don't. What is it plotting? It hasn't even gotten any data to plot. Sorry. But yeah, there's basically a lot of things you can do, and yeah, there reset session, yes, and runtime reset run. Or was it run silent below? And you always need to restart when it's doing pip installs, and then yeah, it doesn't like that. Not sure why we can't do this. Yeah, we could just probably load this in the beginning. So still some things to improve there. But yeah, this just generates some synthetic data sets with causal information in there, and then applies TAPFN as a T-learner, I believe. And yeah, then also sort of outputs the most likely structural causal models, etc. But yeah, are there any immediate questions on this? Otherwise, I would just encourage you to try it out. The Hugging Face gating is sometimes a little bit annoying, so you need to make this account with Hugging Face and then download the model, or you make the account with Parallabs and then yeah, use the API and you don't have to use a GPU. And we might also make this usable without an API token. That would be much easier. Where we're just getting legal counsel about whether we can do that. Because then we collect data and we don't know who it's from, and there's complexities like that. But
not ideal.
No,
yeah, I don't see any questions in the chat for you about this. If anyone wants to ask Frank anything else, I just want to say big thank you, Frank. And even this demo, I think it's really useful for people that are not super familiar with it, and having that notebook is a really good way of starting right with that. So Carlos is asking if you will make training data sets public.
Yeah, so there's a lot of public data sets. We also have nano-TAPFN, which is sort of a small. Actually, I should show that maybe, or if you Google nano-TAPFN, that's another Europe's workshop paper. It's actually a version that trains in 2 minutes on a MacBook for the pre-training.
Wow.
So yeah, it can get you going, and the code is much simpler also than TAPFN. It's sort of like 500 lines of code, and there we're also collecting all kinds of open source priors in order to get going.
Brilliant. All right, so I think this is coming to an end. Thank you very much for this hour and 50 minutes of that PFN, and well, I really enjoyed it, and I think if I say we, everybody will be saying the same thing. Thank you very much. A really big clap to Frank, and thank you for your time. Yeah, looking forward to keep seeing what you do on Tabular Data. Thank you very much.
Yeah, thank you very much, and have fun at the rest of the winter school.
Thank you.
All right, thanks for having me.
Yes, guys. Thank you. All right, guys. So we have 1 hour and 10 minutes break, and next talk is at 2 p.m. From the INSHU. All right, so you guys at the residency should have lunch provided there at the student experience, and all the speakers should have lunch provided at the hotel. The rest of the people that are at home, I will have to cook myself something, right? So
3 o'clock.
2 o'clock.
2 o'clock.
2 p.m. 2 p.m. Yeah, which is only 2 a.m. for her. So
Yes, we are European. Yes, okay. I need to change some things. Okay, see you later.
See you later, everyone. Take care.
Enjoy the lunch.
You.
All right. Very, very good afternoon, everyone. Good evening, then, for you, or good night. Thank you very much for joining back to this winter school. So our next speaker is Professor Bing Xu. She is a professor of artificial intelligence, deputy head of school for engineering and computer science, deputy director of the Center for Data Science and AI at Victoria University of Wellington. And as you may have guessed, she is in New Zealand at the moment. Ben is an IEEE fellow, a highly cited researcher with over 20,000 citations, and she's very well known for her work on evolutionary computation. But more importantly for this winter school is she is for us an absolute hero, because thanks to her, we managed to swap the talk from Friday till today at a very short notice. So just last night, she got an email, and at 6 a.m. on her, I believe, Wednesday, she said, yes, I'll do that tonight. So it's 2 a.m. for her, which I believe is a little bit crazy. And I guess as an expert in evolutionary learning, she has clearly evolved beyond the biological need to sleep. So thank you very much for your flexibility, for being here. The floor is yours. Thank you very much.
Thank you. Thank you. Good afternoon, everyone. Probably for me, now it's good morning, and it's really my great pleasure to be here in the winter school to discuss. And I really like the topic of evolutionary computation for automatic feature and model learning. For me, all machine learning starts from either learning features, manipulate data, or learning the models. Myself, as this guy, I'm in New Zealand. As you can see on my slides, I put 5th of February because my time is not 5th February, and it's 4th for you and 5th for me. So where I'm from, you can see New Zealand is really, really far from Europe, and whenever I travel to Europe, it takes me about at least 36 hours for flights going to Europe. But I do come to Europe every year. My university is Victoria University of Wellington, and we are in the capital city of New Zealand. As they said, it's the coolest little capital in the world. If you going to watch movies these days, you probably see Avatar's made in Weta company, which is sitting in Wellington in the harbor. So here is so I want to talk about evolution computation for automatic feature learning and model learning. So if you're not familiar with it, so evolution computation is a kind of a group of methods, not only one method, that inspired by biological evolution, based on the survival fitness in Darwin's evolution theory. And it is the same as you can say in the optimization approaches, machine learning approaches, as sub area of artificial intelligence. There are many evolution computation algorithms. If I putting them together, I would say that can be grouped as evolution algorithms or swarm intelligence or other methods. For evolution algorithms, that's typically I would say having the genetic operators. So for example, crossover mutation, the typical algorithm, including genetic algorithm, genetic programming, evolution strategy, and other methods. And the other big group is swarm intelligence. So swarm intelligence that including method, for example, particle swarm optimization, that's inspired by the fish schooling or birds flocking. So this as you can see is like a swarm intelligence. And also and colony optimization, which is very good for optimizing route finding, those sort of tasks. There are also other algorithms, for example, differential evolution, mathematical algorithms, or artificial immune system, and evolution multi-object optimization. There are many different kind of algorithms. So the key idea is this is not only one single algorithm, it's a group of algorithms. One of the main strengths is a population-based approach. I'm looking at a paper published in 2015 in Nature. So I usually recommend my students who do not know evolution computation start with this paper. It introduced the idea of evolution computation from a very general point of view. So using very general plain English to describe the ideas. So the paper title is From Evolution Computation to the Evolution of Things. So it basically does not involve too much of a technical detail, but give you the basic idea of evolution computation. So all of the algorithm that I shown you in the last slides can be presented in this kind of a uniformed flowchart. So it usually starts with initialization. It has a sort of evaluation, which is showing how good, evaluating how good the solution is, and then it goes to this what we call is selection. So that's come back to the Darwinian survival fitness theory. So we select a good individual as what we call parents to breeding to the next generation. Using different kind of operators, and then we call it the paper called the variations. Then you go through a loop until the stopping criteria is met. So that's the basic ideas. Then I will talk about why I think evolution computation are a good method to use. There are several advantages for evolution computation approaches. Firstly, it does not really need any domain knowledge. So that means it can be used to solve any problems. You do not need to be a domain expert. You do not need to know the problem or data distribution. It also does not have any assumptions. So whether it's a differentiable or not, it's a linear model or nonlinear, or it's separability. So it doesn't have any assumption. And also it's quite easy to handle constraints. So they are good. A sub area of evolution computation is constraint optimization, evolution constraint optimization. And it can also simultaneously build model structures and optimize model parameters at the same time. So it does not presume any model structures when you're solving a machine learning task. A key analysis is population-based search, which means that the algorithm maintain a population of solutions. So via the iterative search, generation by generation, it finds the optimal solution. And this population-based search also make it particularly suitable for multi-objective optimization. So multi-objective optimization would be like you have multiple conflicting objectives. That means there's no single optimal solution. So the goal is to find the multiple trade-off solutions between the different objectives, where the population-based approach make it to be able to generate a set of non-dominated solution with trade-off between different conflicting objectives. And given all this, strengths, I would say unique characteristic of evolution computation, I think I would say it is a general purpose AI algorithm or general purpose AI system, since it does not tie to any particular domain. And or at least it has a good potential to develop general purpose AI systems. So if I go into evolution computation for many years, it has been primarily used for optimization. So if you search all the papers back to 1990s, there's a lot of work basically using evolutionary computation to do optimization. But recent years, evolutionary machine learning start being more popular than before. So it has been used for address machine learning tasks. However, machine learning and optimization are basically always together. So there has been a lot of algorithm for optimization, but also help machine learning, and also machine learning helps optimization. So evolution machine learning and evolution optimization kind of the same. So basically, I would say any evolution computing method for any aspect of machine learning that can be done. And that's including automatically finding or learning, or if you say evolving models. You can learn the model structure or model architecture, or you can optimize the parameters for a predefined model structure, or you can simultaneously learn parameters and coefficients at the same time. So I'm saying the evolution machine learning has becoming more and more popular these days. And with the topic of automatic feature on the model learning, and so I would say feature basically that is data. So whenever you have a machine learning system, you have a data and you have a learning technique. You perform the learning or training or learning process, you get a model at the end. But one of the key part is the data. So all the features. So I probably don't, we often focus on improving the model, but actually data in many cases, the data can be much more important than learning the model. And the data can also when you're actually solving a real world problem, the data can take you a lot more effort than you develop a model. So I believe that garbage in and garbage out, you really have to have good data in order to learn good model. And sometimes we do see people putting any data and to learn, which basically you can't really learn anything. Some of the tasks are not learnable. And so I would say, and also people have been saying that data determine the upper limit of machine learning. Sorry. And also, sometimes more data can be beats the clever algorithms. And if you link back to those large language models and even come back to ChatGPT or many of those tools, they also, as we know, they trained on a huge amount of data. Without a huge amount of data, they'll not be able to get a good tools. And to improve the data quality or feature quality, there are many different terms on why we are doing feature learning. So, of course, the key thing is to improve the learning performance. It also can simplify the learned model. So that's particularly if you have many features, but not all of them are useful, and then select only a small number of useful features can help you build a simple but a very powerful model. It can also speed up the processing time, and the processing time could be the learning time, it could be also the testing time. And these days also reduce the dimensionality and reduce the cost of saving the data or collecting data, also help visualization. And more importantly, these days we often talking about the interpretability or explainability. This helps a lot as well. And more importantly, is also gain knowledge about the problem, the data itself. So feature learning basically helps basically, I would say basically helps everything that we want. Feature learning can be really complicated, and it can be in very different ways. It can be, for example, neural network, and the first layers are basically we can say is feature learning. And it could also be in other forms of learning. For example, if you have a tree-based model, itself is also basically also doing the feature learning layer by layer from the leaf nodes to the root nodes. And if we're talking about feature learning, I would like you to have a look all of the terms I listed here. So basically, there are so many terms: selection, construction, feature extraction, representation learning, feature learning, data transformation, all sorts of those learning, even feature embedding, and also we call they are feature engineering. So I think some have clear differences, some don't really have clear differences. And I think whatever you wanted to talk about, you really need to be clear what you mean by that. So when I would say all of them can be seen as feature learning. So they all can be under or can be a type of feature learning. So it doesn't matter what model you use. And then when we do when we're using evolution computation to do automatic feature and model learning, for the feature learning part, also often it can be a pre-processing step and can be before you actually model making a decision. And for the model learning part, it can be as I said, model learning model structure. And these days, quite popular research area is, the neural architecture search. That's basically to using evolution computation to find the optimal architecture for deep neural networks. So that can be any kind of network, convolutional neural network or recurrent neural network or even transformers. And evolve coefficient data was some time ago that finding the optimal parameters of the neural network model, and simultaneous model structure and coefficient feature learning. So simultaneous feature and model learning. One of the I would say one of the most popular model and feature learning, model learning, feature learning, coefficient learning, model structure learning is this algorithm called genetic programming, which is one of the main evolution computation methods. There's a task called symbolic regression. Symbolic regression basically is to automatically discover mathematical expressions. That's including the model structure as well as model coefficients. Then for symbolic regression, basically we have a set of data given, and the task is to get the underlying formula or equations that are generating this data. And for genetic programming, that is often build a tree structure that you can use and to directly learn genetic program GP directly learn the model structure from the data, usually as a tree representation. And this tree representation also allows not only for symbolic regression task, but for classification task, for feature construction or feature learning and model learning. So in this case, for example, I have a GP tree here, a tree-based model here. So if I see how it learns features, so it can be used for feature selection, which you can see the tree not selecting all features. It's selecting only 3 features from a large number of features. They can also be seen as a feature construction. So the feature construction could be because the tree itself can be written as a formula or with the operators combined with a original feature. So each of the subtree can be a constructed feature, and the whole big tree can be the constructed feature. You can also see it as a model, sorry, the whole tree as a model. For example, if you're doing binary classification, this could be a binary classification model itself. Usually can use 0 as a threshold and feeding the data value of x1, x15, x42, and then you get the result. You can decide whether it's a positive class or negative class, and which is actually there are many algorithms on the using GP to do binary classification itself. So basically, this tree itself, a simple tree, has been shown as a model learning, feature learning automatically and simultaneously. It's not always like that simple. It can be really, really complicated. It can the model or the feature learning process can be really complicated. So things as we discussed earlier, evolutionary computation or even genetic programming, it automatically generates the solutions. In that way, is when you have a simple problem, it will generate a simple model. When you have a really complicated problems, you will need a model with a sufficient complexity to solve a complicated problem. So it might generate a very big complicated model. So the key idea is basically to learn. It can be any shape, any type of feature, and any type of model as well. If I coming back to the overall the framework of evolutionary computation approach. So again, this population-based approach, and then population initialization, and doing the evaluation, we decide whether it's stop or not. And then there's the generation of generating new population. So the depends on how you're gonna to change the generate the new population. So the algorithm can have different. It can be different. For example, it could be a swarm intelligence algorithm, could be a particle swarm optimization, colonial optimization, or genetic algorithm evolution strategy. So there are many different variations. However, when we trying to use the evolution computation algorithm to solve a problem, I would always say the key part are these three parts. One is the representation. You really need to find a good representation to represent a solution. For example, the previous example we have is a tree-based representation. Right? So the tree decides is a solution. And then the representation determine your search space, how big your search space, and how how your solution can be represented in the search space, and whether how the solution space and the search space corresponding to each other. And then another one to solve a problem, of course, you have your fitness or objective function. For fitness and objective function, that is obvious. That's like basically, if you do neural network, like a loss function and objective function. So in that case, if you're doing a classification algorithm, so you'll probably a task you're probably gonna to have the classification accuracy of F1 measure as the objective function. But if you have a different task, for example, regression, that might probably be the error value, mean square error or root mean square error at the fitness evaluation function. And then, so the fitness value, you have the representation determine your search space, and you have the fitness evaluation function basically determine your fitness landscape. How rough, how smooth that is. You want it to as smooth as possible, so that a small change in the search space leads to a small change to the fitness value, and a large change in the search space lead to a large change in the fitness value. So your search can be like easier better guided by the fitness function. Okay, you have the search space, you have the fitness landscape. Another thing is how you generate new population. This is very critical because this for difficult problem, you usually have a large search space. How are you going to guide your population or your solution to find the best solution? That is entirely determined by the search operators, the genetic operators, or the velocity or position updating mechanisms. So those three key parts determine how good your algorithm is, and determine how you're going to solve your problem. Let's start with representation. For example, feature learning. Let's say feature selection. So it can have, I would say, three or four different types of representation. A very common one is the vector representation. It can be a binary encoding or continuous encoding. For example, if I have 6 features, the dimensionality of the vector is 6, so each corresponding to one feature. So 0 means it's not selected, and 1 means it's selected. And for the continuous one, you can have a threshold to determine whether the feature is selected or not. And then it could be a tree-based representation, as we just shown before. And it could also be a graph representation. In the graph representation, for example, so the collinear optimization usually doing a graph representation. Then you put in the path funding so the feature on the path, that means the feature is selected. Otherwise, it's not selected. It could also be a graph, so a matrix representation. So that is very common in a sparsity-based method. In sparsity-based method, and at the end, you're basically giving a score to each feature, and the one that having high score means it's more important. So you probably want to select those features as your solution, or to train your model. So it can have all the different representations, and then you go to the still following the general evolution computation process. You have the initialization, evaluation, and then but for each of the steps, for feature learning or feature selection, feature construction, there has been many algorithms there available. So then you, based on representation, based on fitness function, they can have the faster ones, which is the filter. You can have wrapper, embedded approach, or hybrid approach. And then based on internalization, when the search space is very, very big, so the initial population where it's sitting is very important. And then how to generate new generation of a solution, that is also really critical. And for decision making, and you having the different objectives, you might have multiple objectives. How you to select a single solution from the pair to front of non-dominant solutions, that is also critical. So sometimes people have a knee-point-based selection, or people can also have ensemble methods to combine all the solutions they obtained from the pair to front. And so we have a survey paper. We basically have 2 survey papers on evolution computation for feature selection, or so that is one published in was about 10 years ago, and the other one about 2 years ago. For the 10 years ago, I think that paper already have over 2,000 citations. And then 2 years ago, we having another review of the more recent work. So if you're interested, if you have a look at the paper, and there's a lot more details there. And then, when we talk about feature learning, and we're also talking about the, in many cases, we may be asked, when we have neural networks, deep neural network, deep learning models, why do we still need a feature learning algorithm or feature selection algorithm? So one of the reasons is, it can be used for explainable machine learning or interpretable machine learning. So this is an example. Basically, what we did is for the image analysis. So then you can see that we firstly we kind of segment all the group of the pixels in the image as super pixels. When have a super pixels, and we're using the genetic algorithm to select the super pixel basically as a feature to be fed to a neural network. So that basically can tell us where the neural network is paying attention to, which part of the image it is used to make the prediction. So that it helps for explainable machine learning. And not only image, we're also working on some of the biological data set. And so that for those kind of data sets, you might have like thousands or 10,000 of features. But the number of examples is really, really small. And it's very easy to cause overfitting. If you fit to a very complicated model, you are very likely to get overfitting. That you get a really poor generalization performance. In this case, that the method that we showed earlier, so the genetic programming method actually doing a very good job. For example, if we're taking the Apple Plus as an example, it having some biomarkers, and the biomarkers is what is a biomarker? Basically, is the one that is a true ground truth result. For this Apple Plus and Apple Max, they have a very large number of features. But for Apple Plus, out of these hundreds of thousands of the features, there are 12 biomarkers that is put it in by the expert. And our algorithm can find 9 of them. And for Apple Manas, so that's that have 5 biomarkers, and the genetic programming algorithm basically can find all of the 5 biomarkers. So the biomarkers determine that whether this having a disease or not. I think it's more interesting that than just finding these biomarkers. Finding them is great. You find the actual root reason for whether this apple having this issue or not. But more importantly, what we found is that genetic programming or evolutionary computing can be really creative, in the sense that it's not only find this combination of 5, it find other combinations for other genes in the gene expression data, but achieve the same 100% accuracy. So that means the algorithm can actually discover some new knowledge that even domain experts was not being able to put it in. They probably might not think about it. So this will give insight to the domain expert for further investigation. And the algorithm we talk about, not only for feature selection. If I'm doing that to make it more complicated, or when you have a complicated algorithm task, of course you need to make your algorithm more complicated. We not only have a single tree, you can have a multi-tree genetic programming. That means one of the method we do that, a single tree, you can easily do the output as finding a threshold as a positive or negative class, based only on the tree output. But if you have a large number of classes, it's becoming more difficult. So you might need more trees or more features to do your task. Here we have this multi-tree representation. In the multi-tree representation, you can easily have in one tree for one class. And then what we can get is, for example, here we have a 3 tree, and the 3 trees, we can having a number of constructed features, a one tree as one construct features. We can also have a number of selected features. For all the feature in the leaf node can be treated as selected features. And you can also have the combination. In many cases, we need a combination of them. The combination that, the selected features and the construct feature used together If you know neural networks, and so this will be quite similar to the idea of skip connection. So you skip the earlier layers of the tree, of the neural network, and to the layer, the skip connection, and here will be quite similar. You using the leaf nodes and the constructed feature high-level ones to fit to the model. And so with this tree-based model, and for many of the tasks, it can actually evolve a simple model that can generate a very good performance. For example, here, and this data set, this, for example, the Cayman data set, I believe it have a 7,000 features. For these 7,000 features, we want to do a binary classification, and the final model we get is just a tree of, it's a very simple tree on the top right, and it has like only a very small number of nodes. So you can see it's a very simple model. And actually select only 4 of the arrangeable features, combine them together. For the 4 features, using a simple arithmetic operators combine, and actually can achieve very good performance. So the magic thing is each of the 4 features, if I plot them here, and as you can see that if I want to separate the blue class with the red class, I will not be able to find a cut point. So basically, if I'm moving all my threshold along this ray, I will not be able to find a point that can say I can find this point that say separate red and the blue class. This is true for all the 4 features. Basically, that means all the arrangeable 4 features are not very good features. However, by combining them using the tree in a very simple way, you can see that actually they can perfectly separate 2 different classes. And this also have a very good generalization performance. And since I'm not a doctor, so I don't know what those features mean. And I would believe if the doctor see it, it can find some relationship between relationship or interactions between these 4 very basic features. And that's the point. I think that those model can provide insight to the problem itself and to help decision making. And as not only that, we talk about this, for making the for decision making. There's also there's often an important point, I think, in many problems, not only for feature selection or model learning or feature learning. There's often we call multiple optimal solutions. Sometimes in evolution computation, some people call it a multi-model optimization. But we do not in machine learning multi-model mean a very different thing, which I will also talk about later. Basically, here basically means that every problem can have multiple optimal solutions. Here I am using the feature selection multi-objective as the number of features and the error rate as 2 objectives. And you can see that the S1 and S2 are sit in exactly the same point in the objective space. If they are non-dominated solutions, that means there are multiple solutions having the same objective value. This is very common, and this is what we call multi-model, multi-optimal solutions. And these multiple optimal solutions can give you some ideas of what you want to, which solution you want to choose, and also tells you why a group of solution and another group of solution can achieve the same performance. Sometimes you can choose from the multiple optimal solution, choose one of them based on your preference. For example, some of the features can be really expensive to collect. You can choose a solution that with features data that is easier to collect. And So with this multi-model, multiple optimal solution, I think that's the key area as well. And then so the application areas of this basically the feature selection or numerical feature learning method is has been applied everywhere. And here just an example for the multi-objective feature selection application. It's just everywhere. You can see. Whenever you have feature, whenever you need a simple model, whenever you want explainability, so you can use this feature selection or feature learning. And so those all basically using numerical data. But there are also some others, when we talk about the model learning or evolutionary feature and the model learning or parameter optimization is evolving neural networks. And this figure I taken from actually a survey paper by Professor Xin Yao in 1999. You can see that 27 years ago. So in this paper, Professor Xin Yao having drawn this figure. This figure, I think the key is when we do evolution computation with neural network, three key parts. The first one evolve of the architecture, evolution of learning rules, for example, learning rate and other part, and the evolution of connection weights, which is the to optimize the parameters weights. So basically architecture, learning rules, and the parameters or learning weights. So that is from 27 years ago. But actually, if you look in the literature today, and I would say all this evolving neural network, evolution computation, and the neural networks, they basically can all fall into these three categories. So, and but it's just two different skills. And in Xin Yao's paper, that is the work reviewed almost like about 30 years ago. And if we're looking at that time, at the reviewed papers like from 1990 or mostly 1990s. Interesting, I find in these slides, and if you're looking at this page, I can point you to quite a few pioneer awards of evolution computation. So of course, Professor Xin Yao is a pioneer award for evolution computing pioneer award. And then the first one, G for optimizing connections and connectivity. And Dara Whitley is also winning the Evolution Computing Pioneer Award. Then you can also see the name of Risto McLaren. He's also a Evolution Computing Pioneer Award. And so you can see all those, these leading researchers, they are working on this area. So that's why I think it's important to bring this area here. So early days was evolving the connection weights, and then it coming to a time that is when we're looking at in about 2000. After 2000, there's neural evolution augmenting topologies, which is neat. That is starting evolving not only the parameters, but it's starting evolving the topology, means the architecture and the parameters. And then there are many neural evolution approaches, and I believe in about 2014 and 2013. And so the Risto McLaren, he have a keynote talk. He talk about so evolution computation is the next deep learning. So there has been a lot of work there. Here today I'll probably mainly talking about the neural architecture search, because that is these days is a really popular topic. The evolving of the weights of deep neural networks is becoming really difficult, right? Because it easily going to millions of parameters in a deep neural network. The architecture seem to be easier to, or seem to be more important, I would say. If I look at There is a really nice figure. So people were saying that in statistical learning, when you actually wanted to or learn it to be generalized well, because we have the basic dimensions or kernel to be high, or have we minimize the structure risk minimization, and also these different functions. They have a really proper model. And at some point, at some times, maybe not these days, people say, if I do neural networks, I want my model to be better. I stack more layers, and more layers and more layers. If not enough, more layers, more parameters and more parameters. I'm sure we can do smarter things, and so smarter things that starts the new architecture search is one of the I will say one of the smart things we have been doing. To do a new architecture search, and apparently using evolution computation, we call it ENAS. ENAS is very popular, and when we're using evolution computation to evolve architectures, and again, I will say again, this is the representation, right? The first thing we're looking at to using evolution computation to solve any problem is to do a representation. So the representation can actually, they have many representations. So basically, it can be a fixed length encoding. For example, using my binary encode, my vector encoding, the dimensionality is the same. But of course, we don't know what is the max optimal depth of the neural network, right? So people have been developing algorithms that can using fixed length encoding to represent a variable length architecture. It can also be a variable length encoding and then represent a variable length architecture. We usually not prefer fixed length or fixed depth of deep neural networks, because we do not know what is optimal depth or optimal number of layers. We always want a simpler model. We do not want to stack more layers than necessary. So to give an example, and this is one of the earlier works that we have done, that this work will basically we started in 2017, 2016, but actually was rejected somewhere, and then we submitted paper to somewhere else, and then we submitted to as in we submitted to transactional evolution computation, and it got accepted there, and I think basically, if you wanted to do a evolution computation for new architecture search, I would really recommend you to read this paper. The main reason is it starts from all the basic component. And I think we have a really nice argument in many different key aspects. For example, there's a variable length representation. For this variable length representation, this is actually, we were in 2017, 2016, we were trying to address the issue of the first evolutionary architecture paper. I think that was by Google DeepMind. And the problem they had is a fixed length representation, and it would not be able to use in crossover operators. And but we know that if you're using GA, you really have to utilize the crossover operator. And if you really wanted to design optimal or architecture, you really cannot fix your depth of the architecture, because the depths or the number of layers really should change according to the problem you want to solve. And then we have the representation we call variable length representation. And the key idea in the representation is actually quite simple. We're evolving convolutional neural networks. So we're doing the convolution layer and pooling layer and fully connect layer. So keeping the fully connect always at the end. And then for convolution pooling, you can basically different combinations. You can different lengths, you're representing different depths of neural networks. And we also having some ideas on the population initialization. That means each chromosome, so we separate to two parts. So make sure it's a valid network after you decoding it. Then for the fitness evaluation, we also using early stopping criteria. And And also we're using train the individual for only a very small number of epochs to save the computation time. And the main reason is from what we observe, so we do not need an absolute value or how good the network is. We only need to know which net architecture is better. So by training only a few general epochs, you already can see which one is better. And then after we got the result, we fully trained the individual at the end. And then we were able to using these crossover operators, and that was one of the issues that the Google paper doesn't have because the variable length. We're using these 3 different ways to allow our variable length to check crossover operator. And we're also using the binary tolerance selection, with the considered number of connections, number of ways to prefer architecture having a small number of connection ways. Another idea that we had is the weight initialization method. So basically, we do not want to optimize the weights or connection weights, but we can have a way to have a good starting point for the connection weights for the before the gradient descent learning. So we're using the Gaussian distribution. That's where the key of what we evolve is we optimize the mean and standard deviation of the Gaussian distribution. Gaussian distribution generates the weights of connection weights, and then the connection weights are trained by using gradient descent backpropagation to train. So this was an early work, but we consider many things that we think is still important to consider when you develop an advanced algorithm. And then, as you can imagine, one of the issues with deep evolutionary neuroactive search is the computation cost. We have a population-based method, which means a large number of solutions and evolving for a number of generations. So then that you involve a very large number of evaluation, and each evaluation you will need to train the architecture to see how good it is. Then what we do is we further develop a one-shot neuroactive search. That basically we build a supernet, a very large net architecture, and then the one-shot NAS is basically we sample subnet from the supernet. So you only train the supernet, but we're using the GA method to fine-tune the supernet. To make it so that since you already trained the supernet, so the fine-tuning process can be really, really fast. And so then you can see the GPU days, we call GPU days that we use for many of the NAS algorithms that can have, the GPU days of 22,000, which is not possible for many of us to run them. But with our one-shot NAS, the GPU days can be less than 1 day. So that is quite affordable for many of the researchers. And apart from the one-shot method, we're also having a zero-shot. For this zero-shot architecture search is here we basically different from the convolutional neural network. Here we're basically using a U-shape network. In the U-shape network, what we do, the task is not an image classification, it's a image segmentation, and more like a medical image segmentation. And if you have, I'm not sure you have background on the neural network for medical image processing. So U-shape network has been really powerful for medical image segmentation for all those U-shape. So that's why in this work we're also using a U-shape network. In this case, you have the encoder, decoder, and also skip connections. And we also using a variable length integer encoding, vector encoding. And this variable length can show the different depths of the architecture for the U-shape architecture. To save the computational time, we're actually using a simple mode and the mobile finite convolution layers. And what we search is we do not search the whole thing, and we search the all the elements in the blocks in terms of number of layers, the expansion rate, and also the kernel size. And so those are parameters that we're using genetic algorithm to search. And we also using a zero-shot proxy. So that means the fancy evaluation is super fast. And for the result, what we get, you can see that basically the previous example I show you, there are evolutionary architecture search algorithm going to over 20,000 GPU days. But by using a zero-shot evaluation proxy, we can shorten the algorithm here. We can actually shorten the time to hours, less than 1 hour. So that's a big improvement. And also you can see the results are looking pretty good. By looking at the results, this is some examples. You can see our algorithm by training a very short time and can identify, segment the key areas that for the second column is ground truth. Very close to ground truth, while other algorithms are not be able to detect those challenging region of the image. And so we talk about the few shot, one shot, and zero shot. So basically these days, one of the key research areas is we getting reduced computing costs in us. So there could be, training free algorithms as well. And they are also cell and block-based algorithm. The transfer learning algorithm, or multitasking, and also multi-objective. Multi-objective can be you optimizing the accuracy, minimizing the number of parameters, minimizing the flops calculation, or minimizing the other criteria that correspond to the computation cost. So this is still a very popular research area for ENAS, and people are starting doing a lot focusing on the reducing the computation cost. So in the last part of the talk, I want to talk about they are not only neural network based method, right? So the tree based algorithm can also do a lot of image computer vision, feature learning, feature extraction, and model learning automatically. Here, one thing is we're using, again, come back to generative programming. So it can do automatic feature learning and model learning. Here is an example for binary classification. So this tree-based model, similar to the network-based model, it can have input layer, input as the image, and then you can detect the key regions in the image, and then you do a feature extraction, feature construction, and then you do a classification layer. So basically extracting from very raw image to extract high-level useful features, and then to feed the feature to layers by layer for feature construction, and then we can feed to serve as a classifier. And this is a very simple example, and but it can also be like more complicated ones. For example, in one of the algorithm papers, what we did is when the task is really difficult, and that previous representation will not be able to achieve a very good performance. Then what we did is we basically separate, we have both feature learning and ensemble learning. For feature learning, that's including input layer, which is we input the image, and then we're using a filtering or pooling layer, quite similar to the idea from convolutional neural network. And then we also having the feature extraction layer, and we have the concatenation layer to concatenate multiple feature vectors. So this whole part is we call the feature learning. And then since the problem becoming more difficult and you have a number of features learned, we're trying to use a model and using ensemble models. Then ensemble learning. So this feature learning and ensemble learning can be in a single GP tree. And in a single GP tree, it will really depends on the task. If you have a simple task, you have a simple tree. If you have multiple, complicated tasks, you might probably get a very complicated tree. So then the feature learning part can have you many feature operators, and the ensemble classifier learning, it could be like different ensemble of different classifiers. This example, ensemble of support vector machine, logistic regression, and the random forest. And then you could also have ensemble of ensembles. So the tree is so flexible, so it can be as simple as only a few nodes. It can be as complicated as many nodes, many depths, as well as many different classifiers, and could be ensemble of ensembles. So there are some further ideas that I mentioned previously as well. So when the model becoming really, when the problem becoming difficult, when the tree becoming deep, there might also lost information from the beginning. And then here we do a feature reuse. If you think about it, it could be like the skip connection that's in neural networks. So you're using the early layer to be the input of the later layers as well. And then here we also allow the tree to have a connection from the early layers to the deeper layer, to skip a few layers in the tree. So that's what we call the feature reuse. In this case, we have a flexible feature reuse. So the GP algorithm will automatically detect whenever we need a connection from the early layer to the later layers. So that's basically the tree can do low level features, high level features, and also you can concatenate multiple layers. So it also decide when the low level features can be directly output to the as input of the classifier. The performance was really good, and we were able to achieve really high performance by having this flexible feature reuse. And then this also have a very good interpretability, because you can see which operator is used and how it's going to use. At each step, what is the result, how is it generated. This is something really, really difficult to achieve when you have a really deep convolutional neural network. But with tree-based models, that you can break down all the decision-making process. And then we also extend the work that can have, multiple trees and multiple trees for the learning features for the image. And you also can have multiple allows multi-skill feature learning. And you can also determine the different color channels. That all can be flexibly encoded in the GP tree to allow it to automatically search and find the most suitable solution. And some more recent work we have been working on, which is more like fine-grained image classification. So the task of fine-grained image classification, so image classification can, if you distinguish a cat from a dog or distinguish a flower from a tree, so that could be the similarity between the different classes is small. But fine-grained image classification is, for example, I have this type of flower, but they are very similar. So we're trying to find the subtle difference between all these very similar classes. What we did here is, we're again using a flexible region detection. That's in the algorithm. So this is this is not a prefixed region detection. It is automatically detected. For example, if we predetermine the key point or key region, you have a different image, so the objects might located at a different corner of the image. So then that's why we did this flexible region detection, where we detect the central part of the objects. Then we crop a region from the central part, then extract feature from those regions. So then your region can be applied to anywhere. That depends on where the object is. Again, this has been achieving a very good performance. And also, again, you can check step by step how the GP tree is making a decision and what each branch is trying to do. Not only that we're doing these doing the images, we also have been working on the multimodality image classification. So the multimodality are most likely very common in the medical domain. So for example, you have the different machines can get you different image modality, MRI or PT. And we also recently encoded the doctor's metadata and to also encode it to combine with the image. That can also all be handled by the single GP tree, generative programming tree, due to its flexibility. And those initial work has achieved a really good performance as well. And so then so it can get all this trees automatically and determine which of the modality is more important and which region we use from each of the modality to help to decide to achieve the highest accuracy. So this is multimodality learning using these generative programming. And we had a book that was used in generative programming. That is probably the first book for GP for image classification, and so that is we call is approach to feature learning. So it's an automatic approach for feature learning, but it's also generated actually with model learning as well. So that is if you're interested, you can have a look at this book. We also having all the code available. That you can, if you want to try, you can try it. All the algorithm that I discussed earlier actually has been in the model. So I have talked a lot about this, from numerical data to image data to multimodality data to learn features and learn models to learn architecture of neural networks. For me, they all be the using evolution computation. They can all belong into automatic evolution, feature learning or model learning category. A bit of all this work, and apparently I have no way to do it myself. We do have a research center. It's called Center for Data Science and AI in New Zealand. So we're probably the largest evolution computational learning group on the southern hemisphere. So you are at different part of the earth. And we are not only doing this evolution computation, we're basically working on many different research themes. So for example, we have data science, statistical learning statisticians in our center. So we have modeling, statistical learning, and evolutionary multi-objective learning. We also have some that are not machine learning, which is scheduling and combinatorial optimization. But I have to say, many of the colleagues on this optimization side these days are using machine learning to help them solve the problem. And we also having a lot of research theme on this image text signal and language processing, video and audio processing. And we also have deep learning, transfer learning, as well as interpretable machine learning. We also, our center was established a few years ago, and then we also start working on this generative AI and also multimodal learning recently, time series data analysis, so all this, and along with what we did, and then we also having this. We at the center or our technology theme, and we surrounding our key and task, also including training, IP commercialization, And we also having various of application domains, for example, primary industry. We do a lot of agriculture. We work a lot with the sea, marine, and we also do working on climate change. We have an Antarctica Research Center. We collaborate, and our colleagues, some of them they go to Antarctica to collect data, and we work on it. And there also we have, public, social, public and policy ethics, as well as, of course, biohealth, medical, and high energy domain, high value manufacturing. And this is all what we have been doing. So we collaborate all with various government agencies and Crown Research Institute, and those basically are rough idea of what we're working on. And so if you are interested, and we are always open for collaborations, and if you are a master student, we always recruiting PhD students and then postdocs on these projects as well. And so. Finally, I really would like to thank all the winter school organizers, and I think you have done a really good job. I think I can imagine the challenges with the weather, but I have been to Granada about 12 years ago, and I really love the city. Whoever, if you are there, and I hope the weather getting better, and you can really enjoy Granada, enjoying the rest of the winter school. I'll be happy to take some questions if you have any.
Thank you very much, Vin. We really appreciate it. Really
Yeah.
nice talk. So there are a few questions already in here in the chat, and I believe Carlos is not able to speak on the microphone, so I will be reading that out loud for you. So he is wondering, what should we do when using an evolutionary approach if the evaluation process is costly? How can we improve the efficiency with not a high impact on the performance of the found solutions? Yeah, I think from there you can continue.
I think you pointed out a really key question, because so firstly, things with images and with large data sets is always expensive. Secondly, with evolution computation that involve population-based and large number of generations, lots of evaluations become even more expensive. I think the key idea that you can working on is to using surrogate model to avoid to do the evaluation. Another one is you could using actually a small number of instances or images. What we found that a lot of our research we say we're working on limited data situations. When there's limited data, this is a point that when we compare deep neural network with evolutionary computation with, for example, generative programming, we found that if we have a lot of data, of course, the deep neural network often works very well. And on the areas like when we have limited data, limited images, evolutionary computing can work quite well. And so then you can find the right application areas where evolutionary computation works well, and to improve efficiency, you can use surrogate models or transfer learning or other method to help you to improve the efficiency.
Fantastic. Tim, you're there. You can unmute yourself and go if you want. I don't know if he's there. In the meantime, Carlos had a follow-up question asking about, is sampling datasets an approach for that surrogate, I guess, that's what he meant?
Yeah, that's definitely an approach. In sometimes we do an instance selection. It's kind of you from the original large data set. You have a large number of instances. we can do instance selection that to select the typical instance representing the original big data set. So by then, sometimes we also call it the surrogate training set, that you can by selecting the representative instances, you substantially reduce the size of the training data, and then you can basically significantly improve the efficiency for the whole learning process.
Great.
Yeah.
Thank you. Tim, you're there.
Yeah.
Under Mario Alfonso's name, but
yes. Yeah. So I guess my question is, is there a way to apply learning methods to guide the search in your evolutionary algorithm? So I mean, for combinatorial optimization stuff, there's neural solvers and stuff exists to kind of help direct and guide that search. So is there a way to apply similar methods to neural architecture search and stuff?
I guess there should be a way that you can do using a learning to guide it. And there are some other algorithms. For example, for new architecture research, there has been learning has been a method that is learning a distribution of the architecture or the performance. And so basically, then you can use the learning to do. So you could using a neural network. You could using a neural network or other machine learning algorithm. For example, what we used to do is we using basically using a random forest or a neural network to build a surrogate model. So you build a surrogate model or build a predictor. Then when you do the new architecture search, you can fit the properties of the architecture to the learned model, surrogate model, to predict the performance, or to compare a pair of architectures. So in that way, you can really you can significantly reduce the computational cost, and then sometimes it can. When you reduce the computation cost, you are able to explore more solutions, and that will also improve the performance of your final solution. So that basically can improve both the efficiency and the effectiveness. Yeah, I hope that answers your question.
That's it, Tim. All right. Is there any other question? I don't see anything on the chat. Right. In the meantime, I found extremely interesting, Ben, your work on zero shot and one shot for NAF. I think it's really, really cool. So I was wondering what you think is going to be next, right? After that, I mean, there is nothing less than zero, right? So I don't know, where do you see the field going from that point onwards?
They say people are doing a lot of training free, right? So you know, to zero shot and one shot is still learning, but the training free means it's not learning. So they are training free proxies. We recently actually, so maybe later on we can share. So we recently also working on the predictors that were for new neural architecture search. That means that we basically do not train, we only predict the performance by building a predictor. That might not be a training free, but there are training free algorithms in neural architecture search.
Great. I think Daniel is also asking there. I don't know if you have a mic, Daniel, if you want to go ahead. There you go.
I'm trying. I'm not very good connection today in the home. Thank you, Yue. Very interesting talk. My question is about usually you have a very interesting GP approach for image processing, but I have the usually in this approach, how you use the multi-objective, in which sometimes it's not so easy to combine. I'm going to explain myself. I have some research experiment in which we allow worse result, numerical result, if we improve the size. And that we obtain that approach improve the accuracy also in our research. I don't know if you consider that this type of approach could be also for genetic programming, because we don't using genetic programming for doing that.
Do you mean using multi-objective approach in genetic programming for image-related tasks?
Yeah.
So that's a really good point. So we have done a lot of work on the GP for image classification, or what type or those sorts of image classification, and we also do quite a lot of evolution multi-objective learning. We actually didn't do a lot of GP evolution multi-objective learning for images. So we did some, but not many. What we found is because the search space is so big, and the GP tree can have all kind of various of forms. There can be multiple very different GP trees achieving the same performance. So the search space is becoming a search space, and the solution space becoming so big, and not one by one corresponding to each other when we're doing the tree representation. And the solution, the objective space can be also very, very messy. And so when we actually doing the multi-objective for image processing, we often end up with not many non-dominant solutions. And so that could be always a very extreme point. That's dominant. Just the part from might only including 2 or 3 of them. So there's not like other tasks you can have a multiple very nicely distributed solution in the part front. So that's why we haven't really did a lot of multi-objective work in GP for image processing. However, it doesn't mean it really depends on if you really need. I mean, if your task you really wanted to see the trade-off between the objectives, then there's of course you definitely it's worth exploring the multi-objective in the GP for image processing. I think it really depends on whether your task needs you to do that.
Yeah. Okay. Thank you.
Fantastic. Is there any other final question? Otherwise, I think we're not going to keep you awake any more time. Thank you very much, Dean, once again for joining us at this time. We really liked your lecture, and we hope to see you soon.
Sure. Thank you.
Thank
you for listening. Thank you.
Thank you very much.
Pleasure.
A pleasure.
Thank you very
Thank you all. We'll see each other at 4 p.m. for the next talk with Anurag from Google DeepMind. Okay? See you in a bit. Go for the coffee. Again, not included today.
Enjoy the coffee.